Warm welcome to all the participants to the final and the sixth day of this AICTE ATAL sponsored FDP on quantum computing and quantum machine learning solutions for a sustainable future. Today, we are lucky and privileged to have a very distinguished person as a resource person, Dr. Anjani Priya ma'am. Welcome, ma'am, to this FDP session. Dr. Anjani Priya ma'am is a quantum physicist with a PhD from IISc, leads AWS India's quantum computing business, and drives a HPC for the public sector. Dr. Priya's journey began as a software engineer at Infosys before earning her PhD from the Indian Institute of Science. As a former technical lead at Soham Innovation Lab, she led the development of an indigenous hearing screening device for newborns. The team earned the National Award for this research work. Later, she worked as a computation and algorithmic specialist in quantum at Robert Bosch. She predominantly works in computational mathematics and quantum algorithms. In the field of quantum, her expertise was primarily focused on algorithmic specialization across various domains, encompassing the automotive industry, aerospace, robotics, drones, computational fluid dynamics, finance, supply chain management, factory optimization, agriculture, material science, drug discovery, and many others. Welcome, ma'am, to this session on behalf of the management of KCG College of Technology, the organizing team of this FDP, and the faculty participants. I extend my heartfelt welcome to this session. Over to you, ma'am.
Thank you, Deepa. Thank you so much. It's a warm introduction. And good afternoon, everyone. I'm Dr. Anjani Priya. I'm a quantum country lead for AWS India. I did my PhD from IISc Bangalore. I predominantly watch this chat window. It will be more interactive session. Before that, may I know how many of you practicing quantum computing and quantum simulations or anything? You can unmute yourself or talk, or you can just type in the chat window. So how many of you already practicing quantum computing? It can be using a simulators, or it can be using quantum computers or anything else. Feel free to type in the chat window. You can vote it. There will be thumbs up, or you can vote it, or you can say yes or no or something. So let it be like more interactive session is this, instead of I'm just presenting the things to you. The entire the faculty development program itself, you to understand the high level picture, so that you will go and start either your research or doing your semester courses or rolling some other elective courses. So there should be some meaningful outcome should be there. If I know you better, your background or your expertise level, so that I can explain you more thing. So, okay, just tell me how many people are new to this field. You could say yes. If you are new to quantum computing, say yes. Out of 43 people, like just in an approximate. Okay, someone is saying just new to this field and a basic level of knowledge. Yes. Okay. In the past the FDP session, you may understand the introduction of the quantum computing, right? The classical and the quantum differences and all those things. I think it covered, but still I'll try to cover a little from my level, from my side as well. Let me start with a few question and answers. I'm again going back to the chat window. I will read the questions and I'll still wait for the answers. Okay, please feel free to be interactive session. Okay. So how many of you know about a CPU, GPU, or on-premises servers, or supercomputers, cloud computing, etc.? Initial few slides, I kept it very interactive, so that I'll take a pass for every question. I'll take a pass for a minute and I'll check the answers. So what is a supercomputers needed? If we have these laptops, we have the desktops, why we require the supercomputers? I'm again coming back to the chat window. We have these laptops and desktops, right? Why we need a supercomputers? Everyone knows it. Like allotment institute have CDAC param machines access, and maybe in your own institute you have a servers which has like the supercomputing clusters. You have it. So why we required computation power? Yes. Parallelism, speed up, processing speed. Yes. Making many computational processing. Yes. So supercomputers are designed to handle, one second, remove this slide. Yeah. Supercomputers are designed to handle extremely complex calculations and simulations that regular computers cannot handle efficiently. It does large scale data processing and analyzing massive data sets in a reasonable amount of time. Okay, I'll give you a scenario to you. Before that, before getting into this question, just help me out. What purpose we do this compute? Just give me some example, like why we require computers? What kind of computation things we are doing it? Some real-time applications where you are using it. So we have a laptops, we have a GPUs, we have CPUs, we have supercomputers, we have a cloud computing, where the compute is required in the real-time things, in the real-time applications. So where is the compute requires? Pharma, drug discovery, agriculture, yes. So just imagine a case. Imagine a case you are doing some algorithm. Okay, Mr. Dr. Hiran Patel messages some pharmaceutical drug discovery. Just start with the drug discovery. Thank you, sir. So suppose you are doing some drug discovery use case, or maybe better you can take agriculture. Okay, suppose I'll just give you a scenario. So there are few. There is a huge land is there. There is a very huge land. There is a very huge. There is a very huge land. There are several gas pipelines are there. Could you please give me a second, please? Yeah, I'll just give you a scenario. There's a very huge land is there. There are so many gas pipelines are there. Suppose if there are so many drones are flying around these gas pipelines, and it will go for the surveillance purpose. Agriculture part will come back, and just let me stick to the gas pipelines. So there is some leakage in the one of the gas pipeline. There is a leakage is going on. So we have multiple drones which capture the pictures. In the back end, we are doing it can be computer machine learning or image processing or computer vision. You're using some technique to classify the pictures, and it will give you an algorithm will give you the exact coordinates of the leakage, so that you will send a rescue team, so that you will prevent that further damage. I repeat again, there is a huge land is there, few thousands of acres. There are gas pipelines. For survival and purpose, you have a drones. It will capture the images. Back end, you have some image processing algorithms are running. You do the classification, and the algorithm will give you the right coordinates of the if any leakage is happening, it will give right coordinates. You will send the rescue team. So this image processing algorithm, whatever you are doing from that collected images, if that is running for 8 hours or 10 hours, that may not be really useful because by the time the gas will be leaked, and so if the calculation is not practical in time.
சார் ஒரே ஒரு பேஜ் பிரிண்ட் அனுப்பியிருக்கேன்.
So similarly, if you have some other if you have some other problem where your calculation is taking more than 100 years of time. Suppose if you are doing a drug discovery use case, take an example is COVID vaccine. The COVID vaccine, luckily we are able to get in few months. Suppose the some vaccination, some drug discovery for the pandemic, if it's coming after almost 10 years or 15 years, they won't be used. So there will be a time frame for any algorithm, a practical time frame. So coming back to the question, you are design such kind of algorithm where your algorithm is running more than a practical time. So what are the options you look for? There is a problem statement given to you. You have designed an algorithm. There are some 1,000 lines of code is there. So this algorithm is executing on any computer. Forget about thing. So on computer, take it an example of laptop. This 1,000 lines of code is executing on your laptop in practical timelines. So what are the options you will go and search for it? I'm again coming back to the chat window. If your algorithm is running more than options in terms of what? Options in terms of what means that's I'm asking you. See, you have written some algorithm. Your algorithm is running. So take an example. Suppose gas leakage is there. If your algorithm is running more than 5 days, so what do? You have written some algorithm to identify the coordinates for that. Your algorithm is running for 5 days. So that means it will not be useful for to identify the right scenario. So you are forced to do the algorithm within the time frame. The algorithm has to run 5 minutes or 10 minutes or 1 hour based on the scenario. So what are the options you can try to do? Divide and conquer. We need real-time algorithms to do this. Real-time data capture, huge data processing. Searching for faster options. Okay, there are a few sensible answers. Just keep give me answers. So searching for faster options. Searching for faster options means what? Either you will do a divide and conquer, like I can give it a technical term for that. You can use a parallel computing where you're distributing the workloads across a multiple processor by using supercomputers. That is what divide and conquer someone means. Next, searching for faster options. Faster option means, okay, I can say that you are using a advanced hardware, but I can say advanced hardware. You are using high performance GPUs or CPUs. You are using advanced hardware. What else can be? First one is a parallel computing where you're distributing your workloads across the multiple processors. And second thing, you're using advanced hardware. What else it can be? Still, your algorithm is running 8 hours of time. By the time entire gas will leak. So what are the ways you'll look for to reduce the time complexity to practical timelines? I came back to the chat window. Feel free to type whatever comes to your mind. That's okay. Just think some other options. How do you can reduce algorithms? I chosen one algorithm. The algorithm is running for 8 hours. Either I do parallel programming and I'll try to do the advanced hardware. What else can be? We need a real-time algorithms to do this. Better I can rephrase it. I do an algorithmic optimization. Algorithm optimization in sense, I try with algorithm 1, I'll try with algorithm 2, I try with algorithm 3. So I will try the multiple algorithms, I'll benchmark it, I'll try to see which algorithm is suitable for me. What else can be? A problem simplification. A problem simplification means, suppose, imagine you are trying to calculate how long it will take to travel every country in the world. It has many complex problems with many variables, such as the distance between countries, mode of transportation, visa requirements, etc. Simplifying this problem could involve focusing only on visiting countries within the particular continent. So instead of exploring entire world, we are fixed to a small continent. In the continent, we are visiting all the countries. We are creating a pattern and we are trying to project it the longer space. So what means? So option number 1, parallel computing. Option number 2, a problem simplification. That means reducing the problem. Option number 3, using advanced hardware. Option number 4, algorithmic optimization. That means we are searching for alternative algorithms. Suppose when you're doing all these things, okay, let's take to one point, algorithmic optimization. So you have algorithm 1, algorithm 2, algorithm 3, algorithm 4. So you're trying parallelly with the multiple configurations of advanced hardwares. So when you are doing this compute, when you need to decide some factor, a combination of things, what really matters? What are the parameters you look for? Which algorithm is rightly suitable for you? Which hardware is rightly suitable for you? So what is the what is the parameter can help you? So which parameter you look for to choose, is it algorithm 1 or algorithm 2, or this computer or that computer? Or I'm doing a sequential programming or parallel programming. How do you decide it? How do you come to a conclusion? This kind of set, time complexity. Else, what else? Time complexity in sense, how much time is algorithm is taking. Uh, that means you need to identify the leakage in the earliest as possible. Time complexity. What else can? Space complexity. Space complexity in sense how many resources we are using it, what is the cost of the resources, how many resources are we buying or paying, and compared to the associated cost, within what time frame we are achieving it. What else? One more critical point. What else? Time complexity, space complexity, what else? When you're doing algorithm, what else we look for it? Accuracy. So how much accurate the results? So three parameters, what we look for it is the time complexity, space complexity, and how accurate my algorithm is. So one last question, how the speed up can be increased? I tried parallel programming, I have used advanced hardwares, I done the algorithmic optimization, and I try to reduce the problem. Still, maybe from 8 hours to 6 hours I got it, or 4 hours I got it. Still, it's not practical in time frame which I required it. So what else I can give a try? And when I'm trading off between the time versus accuracy versus resources versus cost, it's not appreciable. Then we need to think of a different way of doing computing. So in essence, quantum computing is a whole new way of processing information. There are some complex problems that would take a classical supercomputers very long time to solve. However, by harnessing the laws of quantum mechanics, a quantum computer may be able to solve those problems in a reasonably shorter time. That said, building a quantum computer is not an easy task, as quantum devices are very sensitive to influence from its environment. Building a fault-tolerant quantum computer is a big challenge in science and technology. So can I say quantum computers are faster than a classical computers? I'm asking you a question. Can I say that quantum computers faster than a classical computers? Yes or no? Yes. Any other answers? Or any other people support? Yes. Dr. Hiren, yes, and Dr. Sandeep, yes. A quantum computer is not more powerful than a classical one by itself. It's not exactly faster, but it's very different. Although we have a very fast supercomputers these days, there are some problems that we can solve only at a small scale. As the problem size grows, the classical computers would take exponential time to solve. For example, portfolio optimization, drug discovery, material simulations, etc. This is where a quantum computer may be able to help. A quantum computer is not a faster classical computer. Quantum computers follow a different mathematical model, and therefore it requires a different type of algorithms. Many of these quantum algorithms have been shown in theory to scale better than a classical algorithm only when the problem size grows. Look at the illustration. When the problem size is smaller, classical computers outperform the quantum one. The quantum will not give you an advantage. However, when the problem size grows, a quantum computer could provide a significant speed up. So it's faster, it's powerful, but it's not a universal. Only for certain algorithms, certain problem statement, quantum can give you a benefit of speed. So it's not exactly faster, it's not exactly powerful than a classical one. When you have a problem statement smaller, then you will get a better answers in the classical computers. When the problem size increases or a complexity increases, you will get a better answers in the quantum. So I'm coming back to the chat window. So what can be the applications? What can be the applications? Real-time applications where quantum can give a benefit. I'm looking at the chat window. So what can be the use cases where quantum can give you a benefit? Feel free to type. Healthcare, yes. Any other? Agriculture, sensors, yes. Communications, designing of missiles. So these are a very high level, a few potential applications, very high level. A few, okay. A quantum computing is an endless test technology. We are still in an environment where we are doing research and development with these new computers. Quantum computing has a long-term transformative potential. That's why so many industries are paying attention to it. It is still difficult to predict which use cases in which industries are going to be most transformed by this technology. But when we think today about the type of problems that a quantum computer might be able to solve, they tend to fall in three general categories: optimization, machine learning, and simulations. So when it fall under any of these categories of optimization, machine learning, or simulations, there is a chance quantum can give you a speed up. But still, we are we need to test it and identify which use cases will get benefited. And there is no prescription to say these are the use cases, these are the domains will get advantage. Okay, look at the picture. We'll go for one first picture. Okay, there's a cargo container. In the cargo container, there are some few millions of goods are there. So it has a few destinations, take 100 or 120 destinations are there. So it is dispatching from one place. It has to deliver the goods from 120 places and it has to go back. That is the plan. So why I need a computer to solve this? What kind of computational things involved in this? I'm back to chat window. Look at the picture again. In the cargo container, why I need a computer to solve that? What is the computational thing involved in that? You can make some wild guesses. If you see, we are able to focus on the picture, you will able to give some answers. Again, I'm repeating the question. In the traveling salesman problem, yes. So we have 120 destinations are there. What is the best route? What is the shortest route? We can plan for it. Identify the cargo for different places. Oh, that's the same thing. Yeah. Any other? One more important computational bottleneck is there. Look at the picture. It will give you some clue. Shortest routes is the same thing. Okay, I'll just wait for 15 seconds. Load capacity, you're nearby, not exactly the load capacity. You're nearby. There's something to do with the load only, but not about the load capacity. Load capacity is straightforward, right? The any boat or lorry or container, how much it can carry it, it's already predefined. But it's something with the load only. I just wait for 10-15 seconds. Any other guesses? Balancing the load nearby, not exactly. Okay, in which order we are keeping that load? Suppose we have three chairs. The number of permutations the number of permutations, it will come with 3 factorial. That's a 6. If I have a few millions of goods are there, that means I have million factorial combinations, I can arrange these goods. The best way is that whenever the first destination comes, the good should be available on top of that. So that I can avoid it offloading and unloading again. So in which order we are keeping this load? That is a highly complex problem. So similarly in agriculture, when you are manufacturing any fertilizers, suppose if you are simulating ammonia molecules with less energy, there we have multiple simulations involved. In the finance, it can be a portfolio optimization or the trade risk analysis or option pricing, and like fraud detection and all those things has that computational needs. In the pharmaceutical, it can be a drug discovery use case or maybe a gene sequencing or cancer research, multiple things. In the energy also, when we are doing a photosynthesis from the solar cells or identifying the right materials for the batteries, or if you do materials for the carbon capture, and a lot many machine learning problems which can use reinforcement learning, search sampling, and neural network. All these things will fall in the category of optimization, machine learning, and simulations. Okay. So when we are doing this, any problem, okay, I'll go back here. I will go back here. We'll pick some problem, okay? Okay, I'll give you some other example. Suppose someone is designing an aircraft. So when they are designing an aircraft, so there are multiple things will be. They will take one problem. Suppose they need to identify the right set of material. Which material will not melt in the high temperatures when the aircraft is traveling at the lower temperature shouldn't break it. So when they are designing, it can be a car or it can be an aircraft. There is a one problem where to identify the right set of material composition which they can use to build that body of the aircraft. So when in old days they try to take some X material and Y material, they try to mix it to certain composition, and there will be a huge molds are there. They will pour on the mold and they will do the durability, all the things manually. Nowadays we are doing a digital forming. We design an algorithm in that we are feeding this metal and Y metal. Both properties we will give to the algorithm, like what is the boiling point, what is the viscosity, what is the stress, what is the strain, and some other properties will give that the chemical decomposition and everything. So some algorithm will run in the back end. It will identify you right set of the alloy composition in what percentage, 30% X plus 70% Y or 80% X plus 20% Y. It will tell you the exact composition to you so that the metal alloy mixture will be durable in all the temperatures. So whenever we are doing this kind of simulations, don't take me exactly, take with a pinch of salt. I'm just giving you computational, to understand the computational complexity, I'm giving you some random example. In those simulations, you will end up, before that I'll ask you one more question. How many of you try to say benchmarking profile of your algorithm? You do any algorithm. It can be in C, C++, or Python, or Mathematica, or MATLAB. How many of you ever tried benchmarking profile of the algorithm? I'm coming back to the chat window. How many of you tried the benchmarking profile of any program? The benchmarking profile will give you how many times you utilized, how many of you utilize the CPU or GPU, how many times it was interactive with CPU, GPU, and all those things. Just you can try once by looking at the benchmarking profile. Suppose I have 100 lines of code. Suppose I have 100 lines of code. I'll give you one example, which I did it. There is a project where when I was working before Amazon, there was there are few thousand acres, hectares of the berries are there. It's a cranberry land. There are so many cranberries are there. It's a very huge land. So what the customer asked, right? So as it's a very huge land, they can't only depend on the manual workers. So they have so many drones flying on the field. It will take pictures for two reasons. One is that which sector of the berries got ripe, so that they will go and pluck it out. That's the one thing is required. And second thing is that is there any sector of the berries got infected so that they can go and fertilize it. So if they have 1,000 hectares of the land, they can't just go and fertilize it. So whenever a few region got infected, they will go and apply that, and that's easy and easy to manage. So for that, the question what they asked us, okay, it's a very huge land. We have a few thousands of hectares. So we will use drones. Drones are not costly, but the drones has the cameras. The camera will take a picture. The camera will take a picture out of it. So when the camera will take a picture, we'll do algorithms in the back end, we'll process the pictures and we'll try to see and what are the ripe berries and what are the infected berries. Based on that, we'll pass the coordinate to the field workers. They will go and spray there or they will go and pluck the berries. That is a business use case. Now, the question what they asked us, how I can reduce the investment? How can I reduce the investment? Just do a wild guess if someone asked you the same question, because if entire thing, the machine learning algorithm, they're using it, the drones and cameras and manpower, everything. How the very simple question he asked us, how can I reduce the investment? I'll just take a 15 seconds pass. I'll wait for your answer. Just make a wild guess how we can reduce the cost. I'm repeating again. There is a huge land. There are few thousands of drones are there. It will capture the images. It will capture the images. So there will be an image processing. Actually, that's a computer vision problem. They'll do it in the backend. So they will try to get the coordinates of the ripe berries or infected berries, so that they will send the manpower to pluck it out or do the fumigation or anything. So question is simple: how can I reduce the investment? You know what we have given the answer? Use low cost cameras. Drones are generally very, very less costly. But when it comes to the cameras are actually like, because they need a very high resolution pictures and which has to give accurate answers, we advise them to use low cost cameras. When you use a low cost cameras, what happens? The images it will process, it will give to us is so much blurred images are there. So you can't identify from the blurred image. Instead of investing on that many cameras, you invest on the algorithm side, where you are using efficient algorithms which can extract the right image from the blurred image. It's as simple as that. In the computer vision thing, you are taking a picture, some few thousands of pictures will be there. You'll process it and you will try to identify the coordinates. So it will give you blurred images. So from blurred images you are extracting from this one. So if this kind of images are there, when what I did, we try to see that benchmarking profile from where the algorithm, because the whole idea is to identify the right algorithm right now. So there is a one algorithm we're giving a blurred picture. So we need to find the right set of algorithm who can do this, take out the blurred thing out, extract the real image. So in the back end, what it's happening, if you ever try to open the library function, if you're using any kind of C or C++ or MATLAB or any Python, did you ever try to open the library function, what it's calling? Try to do that. When you open that library function, suppose if you're calling some calculations, try to see that library function. If you try to open the library function, what it will generally does, it do some numerical calculations. Numerical calculation in sense, either solve a partial differential equation, or it solve a ordinary differential equation, or it solve a AX equal to B, a matrix inverse or a matrix rank. It do any kind of some linear algebra problem or a matrix analysis problem it does. So if you see the benchmarking profile of any algorithms or any programming, you will see more than 85% of your lines of code will get executed in less than a minute or less than that. Or two lines or a small subroutine or a small function, inside only one or two lines will be there. Those two lines will take more than 80 to 85% of the time. Try to open that library function, check it, why that is actually so much time consuming. You will end up understanding in that single line, it is calling a library function. If you try to open that LBFG or any other library function, if you try to open and see it, it does inside calculating some matrix analysis or linear algebra problem. Take an example, this blurred images. Whenever you try to extract a blurred image, I'll just give a pass here. Just tell me, or you can give me a wild guess. I have a blurred image. I need to extract the image. So what are the techniques I will use it? What are the techniques? You can guess some mathematical techniques. Gaussian filter. Agreed. Gaussian filter is a what I can say is a better, I can say is a application kind of thing. It's a mechanism kind of thing. Inside Gaussian filter, what's happening is a question. I'll apply filter. It can be Gaussian filter, any filter. Inside Gaussian filter, what I'm doing it. So Gaussian, that's what exactly I asked you a question. See, in that specific line, I call it a Gaussian filter. The Gaussian filter will extract. What exactly the Gaussian filter is doing it? Try to open that library function and see what exactly it does. It do the inverse of a matrix. If you have an image, it has a multiple pixels, right? It will convert that image to the matrix. So your pixel grayscale will convert to the amplitude of a matrix. If a higher amplitude, that means it is a darker pixel. If it is a faded one, a lighter grayscale, it will give a lower number. Sorry for this. So you will get a lower number. So end of the day, your image will give you a matrix. From that, you need to do a matrix inverse so that you will extract the right image from that faded image. So entire algorithm for that berry project, what happened exactly is that my algorithm is running more on finding an inverse of a matrix. Suppose entire algorithm, similarly, similar kind of examples will be there in the material deformation also. If it is running for 6 hours, more than 5 or 15 minutes only it's running that x equal to b. Rest of the things will run in just fraction of seconds. That means when you are using any kind of compute hardware, so you are running this one on a CPU or a GPU, you have so much the pipeline for that program. That means you have 100 lines of code. Inside, there are few points where those are computationally very intense. So that means those points are doing a numerical heavy lifting. Maybe it's doing finding a rank of a matrix, or maybe it's trying to solve x equal to b, or it's doing some some partial differential equation or a matrix with some numerical heavy lifting is happening it. So it's like this. You have a Google map, you have a source, you have a destination. So I'm going on the bike. So there will be a blue color path I can see. That means there is no traffic, there's a free flow. There is some yellow color, orange color comes. That means running traffic will be there, slow moving traffic will be there. When there is a red color congestion, that means there is completely block for me. So what I can do it, I can take an alternative path and avoid the congestion and rejoin in the main path. That can be done. So similarly, when you have a heavy lifting on any of the compute hardwares, suppose take an example in this berry project only. So I'm doing some Gaussian filter, In that, it's try to solve equal x equal to b. That is taking lot amount of time. So instead of solving that ax equal to b, that means finding a inverse of a matrix on my regular GPU or CPU, I will upload it to the quantum computer. That means I'm sending only ax equal to b. What is x equal to b? for given A, given B, I need to find X. That means A inverse of B, I need to calculate it. So I will send only this AX equal to B to the quantum computer. I will try to extract this X out of it. I'll again rejoin in the regular path. So similarly, I'll feed this one to the regular classical workload what I have it. So inside the classical computing hardware, whenever you have this heavy lifting, you can offload that specific module or a subroutine to a quantum computer and you can solve it. You can continue this. That means your algorithm or your programming is shuffling back and forth from the classical infrastructure to quantum infrastructure. This is the way quantum computing is all that and a hybrid. Even though quantum computers comes into the in future, most probably it is not going to replace a classical infrastructure. All the time we will go hand in hand with the classical and quantum together. I want to take a small pause here, a minute. I'll look for the questions. Now I just want to give you a very high level introduction of the quantum computing. I'm coming back to the chat window. You can feel free to chat or you can unmute yourself. You can ask me questions. Overfed of shuffling. Yeah, agreed. Actually, like, but suppose you were, that's what where we started. Where you are doing a compute, what really matters is time complexity, cost complex, space complexity, and accuracy. How much algorithm is taking is a time complexity. How much accurate my algorithm is the accurate part, and how much money I'm spending on it, how many resources I kept on it is a space complexity. Suppose if my algorithm is taking a 10 hours time, supposed to be minutes, it won't make any sense for me to use the classical computers. There, the primary focus to reduce the time. If I'm not using a laptop, I'm going for on-premises server. Later, I'm going for a supercomputers or I'm going for some cloud computing. The investment is going just because of either time or accuracy or a space complexity. Here also, you do the similar trade-off. If your algorithm is taking time or it is more costly if it is running for almost 10 years or 15 years or something, there are actually the algorithms will run for years and years. Instead of that, we are making an extra cost or we are making an extra alpha error and we are doing it. The overhead definitely will come, but it will be negligible when you look at the purpose of the problem. Any other questions? Okay, if there is no questions, can I go for introduction of quantum computing? Okay, as this is the last day, just let it be more interactive now for 5 more minutes. Later, it will be one-sided presentation. It will be interactive only for 5 more minutes. Just tell me, what is the fundamental difference to classical and quantum? What is the fundamental difference? When I say I have a classical computer, I have quantum computer. So again, so far what we understand, quantum computer is an extra CPU or GPU to you. So the way you're doing a parallel programming or you're using an extra GPU, similarly, you're using extra QPU, quantum computer or quantum processing unit, CPU, GPU, QPU. So QPU also an extra CPU or GPU for you. That's clear. Now, what is the fundamental difference? Why quantum is giving speed up? Question number one, what is the fundamental making differentiating to classical quantum computers? Second thing, why quantum numbers are giving that much speed up? If something is taking 100 years, how it is solvable in a minute? More data can be processed. Not exactly. Not exactly. Entanglement can be a concept, the speed up concept. What else? I asked the very first question, is the second question answer. Entanglement is one of the concept. And what is the fundamental difference to classical and quantum? You can look at the slide, and I'm coming back to the chat video. Look at the slide. What is the fundamental difference to classical and quantum? Okay, let me ask you a much easier question. We have this laptop, right? This laptop is a classical computer. That's exactly bits versus qubits, exactly. So this is a classical qubit, right? What is a bit in this laptop? What I'm calling a bit in the laptop? This laptop is a classical. You agreed for that, right? So why I'm calling this a classical? I have some zeros and ones. What is exactly the bit in the classical? Suppose I'm typing Anjani, A-N-J-A-N-I, Anjani. It converts A to some ASCII number, some bunch of zeros and ones, some 001110 something. So it will take again N, J, and I. Every operation what I do, everything I type it will convert in the back end as zeros and ones. What is exactly the 0 and 1? How it, that's not a human to write it 0, 1, right? It's an architecture. That means it has some electronic circuits. It has a resistor, capacitor. It has some microcontrollers, microprocessor. If you open the laptop, you will see all those wires and all those things. Further, what is 0, 1? I'll just take 10 more seconds. What is exactly 0, 1 meant for this architecture level? So when you open any classical computer systems, right, it is on the back end, you can see only that PCB circuits, resistors, capacitors, microprocessor, microcontrollers, and wiring, okay? And this database, whatever classical bits, what is this? Not the magnetic flux, it is microcontroller or microprocessor voltage. Whenever you have a high voltage or a 5 voltage, okay, better I say it's a 5 voltage. This 5 voltage is the one which represent 1 for me. When I have a 0 voltage, it represents a 0 for me. That means whenever it takes an ASCII, suppose a 001110, that means every time the microcontroller or transistor will go to high voltage, low voltage, high voltage, low voltage. Whenever it go for high voltage, it in back end it types a 1. Whenever the microprocessor will go for the low voltage or 0 voltage, it takes a 0. That means a classical bit is the voltage in the microcontroller or microprocessor. It's just voltage. Now, so fundamental difference is classical systems have a representation of 0, 1, whereas quantum has a representation of a qubit. Let's go, we'll just go step by step. When we have a microcontroller is still telling me what is 0, 1, in analogy, what is a quantum 0, 1? What can be? Still in the chat window. I'm looking for your answers. If a microcontroller high voltage, low voltage, we are calling a 0, 1. So what can be a quantum bit or qubit? What is the representation of it at the architecture level? Think through. No, gates is the next concept, right? If you have a qubit, with that you are designing a gates. I'm asking you the realization. See, we have a classical bit, 0, 1 is a classical bit. That means at architecture level, a 0 is a low voltage of the microprocessor, 1 is a 5 volts of the microprocessor. That is the way it represented. 0 and 1, we are seeing at ASCII level. So what is the similar analogy in the quantum? I'll just wait for 10 seconds more. Superposition state. No, superposition state is again when the state exists, it's superposed. I'm asking you what is the state itself? What you're calling a state is a question. Okay, let me skip this slide. Let me skip this slide. Yeah, look at this one. So there are multiple technologies people will use it to build the quantum computer. Okay, it can be superconducting one, it can be trapped ion, it can be a photonics one, or it can be a diamond NV centers or neutral atom. There are multiple technologies people will try. So what exactly a qubit, forget about the qubit, what is a bit exactly here? Suppose it is a superconducting technology, they will create a tiny, tiny superconducting circuits, which has an electric current with the absolutely zero resistance. Without resistance, the electrical current will flow in the tiny circuits. In this tiny circuit has a energy levels. So we call those things as a qubit. So whenever I have a microcontroller, give me 5 voltage, I'm saying a classical bit 1. Similarly, in the superconducting technology, when you have these tiny superconducting circuits will give me energy levels, we call it a qubit. Suppose if it is a photonics based. In the photonics space, we use some optical circuits. We will give some laser light on it. So it will go for the beam splitter, optical circuit. It will give you photon means just light. Photon is just light. Whenever we talk about the light, it has a polarization, up polarization, down polarization, or a vertical polarization or horizontal polarization, or up spin, down spin. We talk all these things, right? So they will send these photons to the laser light. It will give through beam splitter. It will give you upward and downward. We call these things are a qubit. Suppose if it is a trapped ion. So we use electromagnetic fields inside a vacuum trap and we'll try to trap the single ion. We manipulate this ion with the lasers. So whenever there is a trapped ion trapped in the electric magnetic without moving it, so it will express some electronic energy states. So whenever this individual ion got trapped, these energy levels will give you a qubit. So we have a classical bits and a quantum bits as analogy. Classical bits are like expression of this transistor or microcontroller voltage. Similarly, every technology has a different representation or different way of building a qubit. Is it clear? Can I go back to the old slide? Yeah. Now, so what we understand. So where we started the question, what is the difference to the classical and quantum? First question, what I asked you, what is the fundamental difference? Is a classical bit is a qubit. What is a classical bit representation in terms of voltage and quantum bit representation based on the technology? There are multiple representation. So what is this qubit? There's a representation agreed in the superconducting. I have electrical current is flowing on it. Mathematically, what is this qubit? I'm coming back to the chat window. Mathematically, what is this qubit? I'm looking at the chat window. What is mathematically a qubit? I'll try to see here. I'm not good in writing, but I'll try to take a pen. Okay, so maybe you know it, but still, I just want to give a completion for that. I'm giving it. So qubits are just a 2 by 2 matrices. So what is the fundamental difference is coming from it? Whenever we have a classical things, we have a 0, 1. These things are discrete in number. I have a 0, 1. Whenever I have this qubits, correspondingly, it is a column vectors. That means just imagine a coordinate space. So I have an infinite number of things available. So better I can say a summation versus integration. That's maybe better analogy to give you. See, when you have a summation mathematically, you go for discrete, right? When you go for the integration kind of thing, you have the continuous. Okay, so classical bits are discrete. You have only two levels. You have a quantum bits is a continuous things. I'll give you analogy. Suppose I'm in the ground floor. I'm again coming back to the chat window. These are only one more slide is there in the interactive. Uh, I'm in the ground floor. I'm taking the staircases to the first floor. So when I'm at the ground floor, if someone asked me to quantify my position, I can say I'm at the ground floor. I'm at the zero floor or zero level. When I'm at the first floor, I can say I'm at the first floor. Okay, first level, one level. Okay, how I can quantify I'm in between the taking the staircases? I'm looking at the chat window. Question is simple. I'm climbing from ground floor to first floor. If someone called me and asked where you are, just quantify where you are exactly. How I can quantify in when I was taking the staircases and climbing up? How can I mathematically quantify it? I'll wait here for your answer. Just allow me 10 seconds. I'll just take some water. Infinite level between 0, comma 1. No, that's not the question. The question is simple. When I'm at the ground floor, I'll take I'm at the ground floor 0. When I'm at the first floor, I'll take I'm at the first floor 1. Exactly. Exactly. So I'm going to quantify it in terms of a percentage. It can be a 40% of the ground floor and 60% of the first floor if I'm tending towards the first floor, or it can be a probability, a 1/4 probability and 3/4 probability to the other side, or it can be an amplitude, or it can be any other parameter. It can be amplitude or probability or percentage. Only these three ways generally we can do. That means whenever you are saying that I'm at 40% ground floor and 60% first floor, that means I'm explaining or I'm representing my state as linear combination of two defined states. So how many that kind of states exist? So how many that kind of states exist? Not exactly four. Again, just go back to the staircases. You are at the ground floor and you are at the first floor. I'm taking the staircases. So as Dr. Hiran Patel mentioned, there is I can quantify a place. There is a 40% I'm at the ground floor and 60% I'm at the first floor. So till that journey, what I'm taking from ground floor to first floor, how many that kind of combinations exist? Look at this slide. Look at this slide, and it's a coordinate system which is infinite exactly. So you have infinite possibilities exist. Classical one, you have a 0, comma 1, only two states. When you are talking about the qubits, in between those two qubits, so in between the two qubits, you have a infinite possibilities exist. So back to the slide. So you have a classical bits 0, comma 1, which are discrete. When you have a quantum, instead of a scalar number, you have a vectors. Whenever you have these vectors, you have a like infinite numbers exist in between this. That's a point number one. Point number two, how many things will exist in between 0 and 1? We have infinite things exist because it's a matrix. In this basis vector states, we have infinite numbers. Okay, so I have a coin in hand. Similarly, I have a coin in hand. When I have a coin in hand, is it a classical or quantum? The coin is resting on my palm. Is it classical or quantum? I'm looking at the chat window. I have a coin in my hand. Okay, it has head and tail. That means there is a deterministic answer. There is a classical. So when As long as coin is there in my hand, that means it's resting, either I can say head or tail, that is the classical. When I'm tapping the coin, when the coin is revolving in the air, there, when any moment, if I try to see that, it has the similar kind of 40-60 or 30-70 kind of combination that is in the quantum. The moment I want to tap it and see, the moment I want to tap it and see, again, the system will go to the classical state. When the coin is in hand initially, suppose take an example, a initial state, it's a classical. It is revolving in the air. I'm doing some operation, it's a quantum. If I want to retrieve the answer, if I want to see the output of it, I need to collapse to quantum to classical state. That is called a measurement. That means whenever you do a measurement, your quantum state will collapse and will become a classical state. Okay, I'll give you one more example. I'll look for the answer. I have 1,000 boxes. In the 100 boxes, I have 100 boxes. In the 100 boxes, there are 99 red color balls are there. Only one green color ball is there. So physical boxes, okay, I have a physical 100 boxes. 99 red color balls are there. One green color ball is there. So how many times I need to open it to get that green color ball? Or you can do any kind of search algorithms or sorting algorithm, bubble sort or anything. That's a different story. Whatever. You can tell me in terms of how many times I need to open the box, or you can tell me in terms of the complexity also, whatever are you. Question is simple. How many times I need to open the box to see the green color ball? I'm looking at the chat window. I'm repeating the question again. I have 100 boxes. In 100 boxes, there are 99 red color balls are there. Only one green color ball is there. To identify the right green color ball, how many times I need to open the box? I'm looking at the chat window. "99 times. Yes. That means, suppose if you talk about the complexity point of view, I have a around n complexity. That means approximately 100 times I need to open the box. At 99, I can see a guess. At 100 time, I can see the box. Okay, so both are same. So if I have 1,000 boxes, I need to see 1,000 times. That means these algorithms will do order of n in the complexity. That means linear in nature. Now let me draw it. So linear in nature. The problem size grows. You can see the linear combination. Suppose if it's 100, I'll see here. If it's 1,000, I'll see here. Okay, this is the linear in nature. Suppose it may not be apple to comparison, but still I have an algorithm which have the ability to see through it. Okay, that means better I can say you are looking at the elevated position. You have that aerial view of looking at the boxes. All the boxes are opened. So how many times you need to query it, or how many times you need to look at that? You are in the elevated position. There are 100 boxes lying just below, only one time exactly. So why it is only one time? Because you are able to create a state, or you are able to see it, all the state in one shot. So whenever you have a sequential manner of opening one box, other box, opening one box, other box, it will demand you order of n complexities. Like 100 times I need to open the boxes. If I have the capability to see through it, or like the elevated position, that means if I have the capability to see all the boxes, all the states at a time, it will give you a reduced complexity. That's the way superposition comes into picture. Similarly, like same thing as said, 40% to ground floor, 60% to. That means by looking at one position, I'm able to see both ground state and first floor, or I'm able to see both head and tail both. That is called a superposition. Okay, so there is one more concept, entanglement. I don't dive deep into that, but very, very high level. Okay, let me erase it. I'm sorry, I never use this. I'll give it a try. Yeah, somehow it's working. Fine. Now, the next question. Go back to this qubit one. Suppose I have a qubit is the 0, comma 1. Okay, we have a qubit is a 0, comma 1. 0, 1. This is a 1. This I'll call it. I could have prepared a slide for this. I'm really sorry for this. Okay, so this is the 1. When we have the bottom one is 1, we call it a 1. When it is a 0 is a 0, comma 1, we call it 0. Okay. Now the question is, if you have a 2 qubit system, okay, I have a 0, comma 1. How many combinations exist? Okay, but I can say I have 2 coins. I have 2 coins. Okay, each coin has a head and tail. If I'm tapping 2 coins at a time, how many combinations it will express? I'm coming back to the chart window. I have 2 coins in hand. Both has a head and tail. How many combinations it will express? Four combinations. That means a 0, 0, 0, 1, 1, 0, 1, 1. Okay. So I have 2 coins. I mean, I want to say like I have 2 different coins. Each coin has the head and tail. That means head, 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 tail, head, tail, tail. So 4 combinations, I'll get it. Suppose you tell me this. I have a XX plus XY, but I can type it there instead of doing all the success here. Okay. Okay, I'm writing the chat window better. I have a XS plus XY. So what is the simplification form of it? X into X plus Y. Okay. Suppose I have a XX plus YY. What is the simplification form of it? It doesn't have anything. Similarly, when you go back to this 2 coins or 2 qubit state, you will express 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. You have a 0, 0 plus 1, 1, or you have a 1, 0 plus 0, 1. You can't take anything out of it. That means you can't make a product out of it. Better I can say you can't separate it. These are tangled each other. That means entanglement. Whenever a state formed where you can't make a product out of it, you can't take a common factor out of it, that is called an entangled state. Generally, the application side, suppose there are 2 soldiers carrying a secret code. Okay, they generally does some person carrying the first half of the code and second person carrying the second half of the code. So take an example, both are carrying a red color balls. Inside the balls there is a code is there. Okay, so both soldiers carrying a red color balls, inside there is a code is there. If a person unfortunately caught by an enemy, if they try to see the box, see open the ball, means like they can paint it or they can open it or they can break it or whatever they can to do to extract the number out of it. Okay, the moment they try to do anything on the first ball, whatever the distance the second ball exists, that will get tampered automatically because this entangled concept. Okay, so there are 2 things. One is that entanglement and superposition. Because of these 2 properties, we are getting the speed up than the classical one. From here, there won't be an interactive session, so it will be one-sided. Just if you feel so boring and just feel free to stop me and discuss. So similarly, we have a, so now let me summarize it. What is the fundamental difference to classical and quantum? The way we are representing the bit, the way we are generating the bit, that means the way we are building the bit. Higher with the transistors one side, therefore trans are superconductor different side. Second thing, classical bits are discrete in nature. Quantum bits are continuous in nature. These are discrete numbers. These are vectors. Next concept is because of the superposition thing and entanglement, we are getting that speed up. So this is the programming, very high level programming. This is when we have electronic design and assembly language, we have AND gate, OR gate, XOR, NOR gate. Similarly, we have a quantum gates. But we have a 2-qubit system all the time. That's why we have 2-qubit. But still 1 qubit also available. If you take a head mat, like suppose you have a 0 and you have a head mat gate, it will give you a superposition. The head mat gate will give you a superposition of it. Okay, and this is how the quantum software looks like. You have some initialization, you have followed by multiple gates, and you will get some output. This is a quantum 1, this is a quantum 1, 2. That means you have some vectors here, you have vectors here. This is like a coin is rotating. If you want to see the answer, you need to tap it up. That means from here, it will collapse the classical state once you do a measurement. So finally, these are the key concepts you need to understand. What is a superposition? What is an entanglement? What is a quantum gate? What is a quantum circuit? What is a coherence? What is the error correction? What is algorithms? Yeah, this is the previous slide which I used it. I'll take a pause here. Now I will get back to the what we are doing at AWS. Can you take a pause and look for the questions if you have any?
semester के तो मैं अरे एक ही है अरे एक पढ़ा अभी वो प्लस 2
Okay, if you don't have any questions, I can move to the next part. What Okay. No problem. Okay. So in Amazon bracket, we have 4 different pillars are there. Amazon brackets, a fully managed service. I'll explain you in detail. And second thing, we have Advanced Solution Lab. In Advanced Solution Lab, this is more for funded projects or industrial projects. Take an example. Suppose an industry or a research lab, they got some grant and or they want to do some POC. They don't have a experience to do this, but by making a POC, they will try to explore further. So the solution lab has the expertise from HPC, AML, quantum all together. They try to create a POC out of it, and they will try to explain the POC to the customer. This is a paid service. Next, AWS Center of Quantum Computing. Which one? AWS Center of Quantum Computing, where we are building our own quantum computer with superconducting technology. And fourth one, the post-quantum cryptography and quantum networking team, where we talk more about the networking security aspects and post-quantum cryptography. So this is the 80% of quantum computing. So far, we are able to build one logical qubit. There is a difference to physical qubits and logical qubits. To build a physical qubit, you need a few thousands or hundreds of physical qubits together. So we are able to achieve one logical qubit so far. So coming back to the Amazon bracket, before getting the Amazon bracket, I'll just go back to the previous slide. Okay, so there are different technologies available to build a quantum computer. So it can be superconducting, photonics, ion trap, or neutral atoms, or anything. So how do you know which technology will be useful for you? There are multiple computers available at different scales. How do you decide which quantum computer you need to use it? Maybe this is the last question I may ask you. Okay. I'm coming back to the chat window. Question is simple. There are multiple technologies people are building it. That means there are multiple quantum computers are available at different scales, maybe different number of qubits. How do you know? How do you know which quantum computer you need to pick it up and use it? Any guess? Yeah, so there is no prescription to say, point number one, which technology can build a universal quantum computer? We don't know. Maybe because of the scalability, superconducting qubits has a more qubits, photonics has a less qubit, maybe, but still there is no prescription to say which technology is building a universal quantum computer. That means everything is in the race. We don't know who are going to win the game. Second thing, even though we have a multiple quantum computers are available, we don't know which quantum computer will be useful for a specific use case. We are in a situation where we need to test it and understand which quantum computer, which simulator is giving a benefit for our use case. For example, in the healthcare sector, there is a group of people working, a drug discovery people are working it, and some people are working on the genome sequencing or DNA sequencing. If they use superconducting, a few people, it may give you a better results than a classical one.
Ma'am, excuse me.
Yes,
Ma'am, actually the slides are not visible now. Can
that
you
is not
reshare
visible.
once again?
Yeah,
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 yeah.
sure. One second. Yeah. Thank you. Thanks for letting me know. It is shareable only. Maybe I need to drop it off and come back, ma'am, because it's in
Yeah, I
shareable.
think so. The
Okay,
settings
so
have changed, ma'am.
let me leave and rejoin. Excuse me
Yes,
for
yes.
this.
Thank you, thank you. Yeah, thank you, thank you. Yes, ma'am. Now you can share. Yes, ma'am. Perfect.
Thank you so much. I'm audible to you, right?
Yes, madam. Yes.
Yeah. So, the question where I asked you last one, like, if you have a multiple, if you have a multiple computers are available, how do you know which computer you need to choose? So suppose I have a problem statement to do a drug discovery use case. Suppose there I'm doing a protein folding algorithm. So I just want to give a try for the superconducting systems. Okay. So someone offering a superconducting system. So I will, because it's a 6 months project or 1 year project. So what I will do, I will go for the long-term subscription. In the long-term subscription, I will enroll that one. And later I will try to see the documentation, try to read the documentation. Still, it is a Python code, but still it is a different kind of syntax will comes, right? So I will try to understand the syntax and I will do the programming. I'll run it. Later, there is a point where I realize that superconducting technology may not giving a results for me. I need to do the same thing with the Android technology. So what I will do, I'll repeat the same thing. I will again go and subscribe. I will pay a 1 year fee in advance. I'll subscribe it. I will read the documentation. I will learn it, I'll train my students, and we will do it and we'll compare the both. Suppose again, if I want to do a photonics based, so I need to repeat the same thing. So what we believe in that, we have on Amazon bracket, we are facilitating multiple quantum computers in one place. It's a fully managed service. We have 7 different quantum computers from 4 different vendors. So here, it is a very, very simple Python code. you are changing only one small endpoint. Instead of calling a same Python code, there is a one single endpoint, you're changing it. Instead of mentioning a device as ANQ, you are mentioning as a Rigidity or IQM. The same notebook you are submitting to ANQ and Rigidity and IQM, or maybe ARIA or Forte or Anka 3 or Garnet or Emerald. For these 6 quantum computers, you are submitting it, you are comparing it and understanding which one is giving more benefit to you. So fundamentally, it's a fully managed service. It will take care of all the scripting things. You are writing in a simple Python language. You are changing only one small endpoint and switching over in between the different hardwares. So there are multiple ways you can interact with it. You can do Amazon Bracket SDK, or you can do the Jupyter notebooks, or you can do the command line prompt. So there you can test it and simulate it on multiple simulators and QPUs, and with you can compare it and you can benchmark it, and still you have the access to combine the quantum and the classical resources together. And there are tools exist where you can monitor your algorithms and you can analyze it in the real time. You can test that performance. So these are the hardware available with us. We have a from INQ, we have ARIA Forte Enterprise with the 2536 qubits. And Regity, we have a Anka 3 with 84 qubits. IQM, we have a Garnet for 20 qubits and Emerald for 54 qubits. And QERA, we have a Aquila with 256 qubits. So there are two different categories. The first three are, the first 6 QPUs are gate based. That means let me go back to this previous slide. So whenever you are able to write something or break up in something, or there is input, there is a output, in between there are algorithms which break it up in terms of combination of any, we call the gate based. So that we have a maybe if you are heating up an hydrogen atom, it will express that in terms of what is the energy state, first excited state, second excited state, like that. Or suppose if you're doing like Lagrangian simulation or Hamiltonian simulation, better I can say e power minus IHT, all these things will come onto the analog part. Now, these things will comes with a cost, and there will be a very large queue will be available. Thus wise, we bought a simulator into picture, because most of the users are coming from the research and academia. So they are new to the quantum and they try to understand which quantum computer is giving a benefit for them, how to start it, how to program it, and all those things. That's why we bought. And again, till the last year, these quantum computers are not available all the time. So these were available only 2 hours per day. So you need to wait for those 2 hours. So now it is available almost 24/7. Then we bought a simulator into picture. We have two different categories of simulator. One is a local simulator. The local simulator is where which you can install to your local machine. It's completely free of cost. It can simulate till 25 qubits. And we have a 3 different on-demand simulator: state vector, tensor network, and density matrix simulator. State vector simulator can simulate it for 34 qubits. Tensor network simulator can simulate to 50 qubits. And we have density matrix simulators can simulate to 17 qubits. Suppose if you want to do something on the graph based or quantum machine learning algorithm, or if you are using something a structured graph where you have a edges and vertices and all those things, this better tensor network simulator will give you optimal results. But still you will get a good results on SV1, but you will get the optimal results in the tensor network simulator. Similarly, we have a state vector simulator which can be useful for you predominantly if you want to do a state vector calculations or amplitude or expectations value and all the things. And a density matrix simulator. So when I call it a simulator, means these are not a quantum ones. These are a quantum mimic ones. These are a high performance computer based where we are hard coding it back end so that the results will come in the quantum like. It will act like a quantum simulators, but these are HPC simulators. So whenever you have a real quantum computers, you will end up with the noise effects. That's why we bought the density matrix simulator. It simulates up to 17 qubits. It will give you that noisy effect of it so that it's easy for you to understand how the noise is working on it. So what we can give you an advice, start with the local simulator. It's completely free of cost. After this, I'll share the materials with Dr. Deepa. You can use that material, install the local simulator, or advise your students to install the local simulator, start working free of cost. Later, move on to the hard on-demand simulator. These are very low cost. These are 0.075, very less cost per a minute. You do it, test it, debug it, look at the circuit, look at the answers. If you have a degree of confidence, then on the same notebook, change only one single word or one single line. Instead of taking SV1 or TN1 or DM1, you go and change it to ANQ or REGT or IQM. So your notebook remains same and you are changing only one endpoint instead of submitting onto the simulator. You are submitting on the quantum computers. The Python notebook remains same. Now, as I told you, the Google Map example, most probably, maybe I can say all the time, these are hybrid in nature. You need to shuffle back between the classical infrastructure and quantum infrastructure together. What happens? You will end up with the required a lot many tools. Tools in sense. One second, please. Yeah. Tools in sense, suppose take an example, if someone is doing a biochemistry or microbiology, if they are doing a protein folding algorithm or DNA sequencing something, they generally use a MATLAB to do MD simulations. Okay, so they do half of the calculations in the MATLAB. Later, there is a computational bottleneck compute picture, like similarly the way which I showed you earlier. This kind of thing. So initially I do on the MATLAB, there's some computational bottleneck will come. This one I upload it to quantum computer. I'll get this one, I'll feed it back. Okay, so similarly, if you are coming from a computer science background, you may require a CUDA-Q. If like similarly MATLAB, CUDA-Q, if someone is doing on the Qiskit or Penny Line, these are completely integrated, and you can do with a CUDA-Q, QBride, Penny Line, Qiskit, or you can do the MATLAB, or you can do with the Julia. All these things are completely integrated, and we have a like a generative AI assistance. It won't do you complete programming, but if you have a repeated task, you can use a Claude 3 Bedrock. It will do the automatic programming for you. I can share the details with you after this session. So these are a few national quantum initiatives outside the country, and this is especially for in India. We concluded this program already, but this is a very good example to see. We have with the Ministry of Information Technology, we have a quantum computing application lab where we ran this program for 3 years, and we concluded this one in the May 31st. There we invited the people, faculty and startups to submit the proposals. The selected proposals got the credits from Amazon. They have a almost 1 year, 2 years validity for that. And when we started this, except 1 or 2 faculty, what we understand, almost major people are from a non-quantum background. There are people from AML background, data science background. There are people from ECE, electrical engineering, and there are a lot many people from the biochemistry, microbiology. They don't have a much idea about what is quantum. So then we ran this program it was a project duration of approximately for 2 years. There I personally gave more than 300 plus hours of training. There, we explain them what is the cloud compute, what is how to use a cloud. Later, what is a quantum computing, what is the difference to classical and quantum. Later, we explain the programming. Later, we explain the algorithms. Later, we created small clusters. In the clusters, where we explain them, like suppose the cluster is coming from quantum machine learning. We have invited the people to give a introductory session on the quantum machine learning, where a student, a research student, and coming back and showcasing a notebook which is built on Amazon bracket. So it was very constructive learning hours. In last 10 months, from this group, there were more than 90 plus publications where they started majorly a non-quantum people. The group right now in the audience, a similar kind of group where a lot many people didn't even know the quantum computing course as it is, and all are done a very good hard work and then a translated research. It can be cybersecurity, it can be agriculture, it can be traffic optimization and drug discovery, a lot many. There are more than 90 plus publications came. This is one of the example from the RBCE college. The faculty did the protein folding by using variational quantum eigensolver. They got very good results on the quantum computers compared to the MATLAB. And they did a MATLAB and bracket integration together. So apart from like what other people are doing it, see, one set of people are researchers where they are the fundings and projects from, it can be from CSIR, MIT or DST or SERP. They have their own projects that they're doing research. And a lot many places where faculty is offering a semester course, a 2 credit or 3 credit course, where it has a lot of theoretical thing, and they have the 50% hands-on and the Amazon bracket. So behind the university is the one where we started. Now a lot many colleges are running the quantum semester courses with a 50% on theory and 50% on the hands-on experience. So where we can suggest you, if you want to offer a semester course, go for a customized course instead of imposing entire quantum as a thing. Suppose if you're offering for cyber security or biotechnology or data sciences, a foundation course will be same. Later you can customize the course. What are the relevant algorithms can give you benefit in that specific field? You can customize the course and you can offer it. So how to start a journey? I request you everyone to take your mobiles and scan these things. I'll share you some QR codes. Again, I'll give you the URLs as well. So this is the bracket learning digital batch. We have introductory and advanced self-paced courses completely free of cost. It will be approximately 4.5 hour training. It's a digital batch. You can complete the you can complete the course and you'll get this digital batch. Hope you have taken the QR code. I'll just wait for 10 more seconds. Or like if someone doesn't have a phone in hand, that's okay. I'll share these details with Deepa. She will circulate with you. Next one, this is the bracket direct. If someone is aggressively working on quantum, if the queue time is difficult for them to wait, there you can reserve the instance, reserve the quantum computer for much advanced for hourly basis. This is a bracket direct. So these are Amazon bracket examples. We have a GitHub repository available. We have a few introductory courses, and we have algorithms, and we have advanced modules for quantum machine learning, optimization, pulse control, cascade, and everything. So you can, one second. So let me try to unmute them. Yeah, thank you.
So it is muted. Yeah. Yes, ma'am.
So these are the Amazon bracket example where you can there is already prescripted things are there. You can work top of that. I can give you all these details to you. We have the blog post where it will give you if any suppose if someone started newly, suppose take an example, if JP Morgan started or some other pharmaceutical company started an Amazon bracket, you will see all these blog posts. It will give you kind of case studies, which kind of industries are working, what they are working, and it will give you if any like national level programs are happening, or sometimes it will give you if any new hardware is coming up. This is mostly for the industrial people. We have a Quantum Embark program. It's a 12 weeks program. It will be 12 weeks program where people will give you dive in deep and is identify the right use cases. It's mostly for the enterprise and industries. So these are all the slides together. Okay, I think it's I can give the that's all. That's all. Like I can conclude the session here. I'll share you all these QR codes or the digital badge and different things with Dr. Deepa, and Deepa will circulate to you. Or you can, here is my LinkedIn ID. You can connect me over the LinkedIn. If we are conducting monthly workshops, generally it's tough for us to communicate through mail. We will announce a monthly workshops in the LinkedIn only. So generally we conduct a monthly workshops, like every month we'll come with a one different country time zone. In the monthly workshops, where we'll give you access to the console. It will be like 24 hours or 48 hours, sometimes 72 hours access will give you. With the upper cap will be 500 people has to be registered. Like so we'll give you this kind of introduction. Parallelly, we'll open that console, we'll explain your notebook line by line. But that advertisement generally we do by LinkedIn because it's very, very difficult for us to communicate over the mails. So that you can take this LinkedIn thing and we will share you whenever that kind of monthly workshops comes in India. So better I can conclude
Thank
here.
you. Thank you so much. And I'll be sharing your PPT to the participants. It will be very useful for them.
Yeah, definitely.
Thank you for accepting our invitation. And amidst your busy, very busy schedule, we are in fact very lucky to have you with us quantum computing and how to execute the programs in the quantum computers. Ma'am has given us so many leads and
I think this some voice is breaking. I can't hear you.
We'll go to the next session by Dr. Tejendra Dikshit, sir. Sir, are you online?
Thank you, everyone. Thank you so much.
Yeah, hello, madam. Yeah, I'm online. So
Yes, sir.
I'll just share
So
my
your voice
screen.
is
Yeah.
clear? Yes,
Yeah,
yes,
yeah.
yes, yes.
Am I audible?
Yes, sir. Yes, sir.
Okay, madam. I'll just share my screen.
Before that, there's an announcement for the participants. We'll have the valedictory session. We have one more session by Dr. Kumar Gautam, followed by the valedictory session. After the valedictory session, the attendance is mandatory for all the sessions, and we will be having the test as well as the feedback will be taken from all the participants. Both the test as well as the feedback is mandatory for everyone for getting the certificates. So the slides are clear, sir?
Yeah.
Yes.
Can you see, madam, the
I
slides?
now, yes, we can see the slides. I invite
Yes.
Renuka to. Renuka, are you there?
Yes, ma'am. Yes, ma'am.
Yeah, please introduce our chief speaker, guest speaker for today's session.
Yes, ma'am. It is now my pleasure to introduce our next speaker, Dr. Tejendra Dikshit. Dr. Dikshit is an assistant professor in the Department of Electronics and Communication Engineering at the Indian Institute of Information Technology, Design, Manufacturing, IIT DM Kanchipuram. He earned his PhD in Electrical Engineering from IIT Indore and was a postdoctoral fellow at IIT Madras. His research focuses on two-dimensional materials, metal oxide nanostructures, nanoscale optoelectronic devices, and quantum devices. At IIIT DM, he has established the Optoelectronics and Quantum Devices Laboratory, guiding undergraduate and postgraduate research. His current work spans photonic and neuromorphic computing, light matter interaction, defects, and interface engineering, memoristive devices, optically tunable memory elements, and hybrid quantum devices. Please join me in welcoming Dr. Tejendra Dikshit.
Okay, thank you for this introduction. And I would like to thank Deepa Madam for inviting me and giving this chance to present some of my work. Okay, so today I'll be talking about something called quantum intelligence, and we'll see how can we attain that with the help of photonic technology. So firstly, anyway, I hope you all have gone through by now a variety of things related to quantum computing, but I'll try to cover the three major aspects of quantum technology, I would say. One is the fundamental physics part, which is quantum mechanics. Then the key terminologies which are needed, especially to understand superposition, entanglement, and coherence. And then we'll talk about quantum circuits and quantum gates, followed by quantum algorithms. So I hope you all are anyway aware that it all started around 125 years back when Max Planck has come up with a solution for a very interesting problem, which was obviously uh, was a very major bottleneck for the conventional classical mechanics, especially in the late 18th century. So the issue was, for example, you take a black body, okay, and you start heating it, and definitely at a particular temperature, the kind of radiation which is being emitted by the black body will be correlated. Like say at like say 300 degrees, 3000 degrees Celsius or 4000 degrees Celsius or so on. Based on that, the color of the color which is being emitted will be correlated, highly correlated. And to justify that, like say based on the temperature and based on the what kind of wavelength is being emitted, there is something called Wien's law, or also given by Rayleigh and Jeans. So they have given one formula. With that, we'll be able to justify how things are changing. So the existing classical mechanics, if you talk about, was able to convey or able to follow the pattern, especially in the longer wavelength regions. So that's how the dotted line is actually what they have predicted as per the classical mechanics. But experimentally, if you see, the graph will be like this. Uh, it will always have a peak, and once we are moving towards very lower wavelengths or very high frequency ranges, there is a decline, and which is obviously you can say logical pattern, logical trend. But as per classical mechanics, what happens if you are going towards very lower wavelengths or higher frequency ranges, then theoretically it should follow this kind of pattern. uh, just a minute. It will start following a pattern where it is keep on increasing. So that is one major problem which was there, and Max Planck came up a solution for this particular issue, and he proposed that instead of having a continuous exchange of energy between the electrons present in the black body and the surrounding, they are going to interact uh, or going to receive or dissolve the energy in terms of wave packets or some discrete packets of energy. So that's one solution he proposed, and that was the founding stone of something called quantum mechanics, where we assume that we understood that okay, things are not only continuous; these are going to be discrete in nature, especially at the nanoscale or atomic scale. So I'll come to the next point. This is one breakthrough which happened in 1900 century, okay, where he proposed this. And since then, the next major breakthrough happened when Albert Einstein gave this photoelectric effect. And there that time, obviously there was a you can say two different theories are there, especially related to the wave nature and particle nature of the light. This with the Einstein theory, they again understood that okay, this particle nature is prominent, and there are certain phenomena where this wave nature is being justified. So this dilemma was going on, and in 1925 or so, de Broglie has given this concept of dual nature, and with where he justified that not only the light, variety of even everything will have certain wave characteristics, even if it is a particle, and if it is a wave, it will have certain level of particle characteristics. But the probability can vary based on what regime we are trying to explore the particle or the matter, as well as the wave component. So these are some basic things which happen in the classical mechanics. Now, if we talk about a very if we talk about the quantum application part, like say how things have started and all, so that was actually given by Richard Feynman, a very famous world-renowned physicist, and he gave one statement that we can, if you really want to explore nature, really want to understand nature, then in that case you need to do the simulations using quantum mechanical systems. We should be able to utilize or harness the behavior of quantum nature of matter, and somehow we should be able to utilize it for mimicking quantum behavior. So this is what he proposed, and that is assumed to be one of the founding lectures uh, given for the development of quantum technology, or nowadays this quantum computing part. So if we talk about the applications, I'll just move it. If we talk about the applications, so nowadays, a variety of applications are there which are related to quantum. Okay, and one of the starting applications, if we talk about, are lasers and transistors. Still, if we talk about the core quantum applications, for example, where we are utilizing GPS, or where we are talking about quantum computing, or quantum cryptography, or say superconductivity based squid VSM, these kind of systems, if you talk about, or atomic clocks, these are mostly quantum. Okay, though lasers, transistors, these are also part of quantum, but scientific community generally do not consider them as a you can say as a direct application of quantum. They are utilizing certain behaviors of quantum, but in order to be actually classified as something under this umbrella of quantum computing and quantum technology, they should follow three stringent criterias that we'll see in the coming discussions, which are nothing but superposition, entanglement, and coherence. So variety of things you can see are related to quantum, and because of that, there are variety of you can say startups, companies. I think in the previous meeting already you have seen Amazon has already come up with a variety of solutions. So not only Amazon, I would say a variety of startups are there. But now why we are moving towards quantum? That is the major question. What is the reason why we want to explore quantum aspects, and what is the necessity? So if you talk about, I'll suggest it from the semiconductor technology perspective. Why? Because ultimate aim of any this you can say the society is to replicate things which are already present in the nature, because the things which are there in the nature are highly efficient. Okay, because these are optimized over the period of time, and that's why you'll always find the most optimized systems in nature. And if you want to replicate that, for example, if you want to replicate the behavior of human brain, or if you want to replicate very large number of computations, or very unique kind of say understanding, for example self-adaptive learning, or say complex processing, or say natural language processing, these kind of things can be easily developed if you are moving away from the conventional silicon technology. And the reason behind that I'm going to discuss in the next slide. But those things can be easily achieved if you are talking about quantum technology, or optical technology, or say this DNA technology. And this is one of the trend which we are seeing. Now we are somewhere here where we are talking about 3 nanometer node technology, and research level we have already gone up to sub nanometer node technologies. But the major problem is conventional semiconductors cannot work in this particular domain. And we being obviously human beings want or crave for much better, much efficient systems. So that's very clear that if we continue with silicon or continue with the conventional technologies, there is a limit now. We have already reached up to that border. So, and this is not the only trend. If you see the trend given by Intel, we have already reached up to theoretical, means not theoretically, this experimentally also we have reached up to a 2 nanometer no technology. Okay, so that's the major problem. Why? And the major thing is, see, if you are keep keep utilizing silicon, keep utilizing conventional semiconductors, the functionalities are going to be limited. Okay, so to overcome that, people have come up with new kind of technologies, and one such thing is quantum technology. Now we'll talk about certain aspects of quantum. Okay, so one thing is very clear, that because conventional technologies have already reached up to their saturation, especially you must have heard about something called Moore's law saturation. Okay, which people have already predicted in 2010 or so, and now it is by 2030 or 2035 will not be able to extend or go beyond that. So that's the major problem, and now that's the reason why people are moving towards this development of quantum technology. Now we'll talk about some basic overviews or basic things which have happened, and then we'll try to correlate from the language of quantum. Okay, so there are two important lectures given by Feynman. One I already have discussed with you, that in 1981, 1982, that conference, he proposed that we have to simulate the behavior of nature using quantum mechanical systems. And this is one lecture. And the first lecture he gave in 1959, which was the founding stone of nanotechnology. So there he told that there is plenty of room at bottom, and which was obviously was you can say the key point from where the nanotechnology or this quantum dots or nanostructures and all sorts of things have actually started. So if we talk about the overall progress, how things have evolved in quantum, so there are two important areas. Um, First is between 1900 to 1930. That era was defined as golden time of quantum mechanics, where all the theories have been given. And for example, in 1900, Max Planck has given this quantum hypothesis that energy is quantized actually, and the interactions are happening in a quantized way. And then 1905, photoelectric effect has been given by Albert Einstein. Then a major breakthrough happened when Niels Bohr has given his atomic model. And after that, de Broglie has given in 1923 to 1924 the idea of dual behavior of matter or particle. And then after that, in 1926 and 1927, also some interesting observations happened, where in 1926, Schrodinger has come up with Schrodinger wave equation, where he has given the solutions of the quantum states which are present. That was there in differential equation forms, and Heisenberg has come up with his own way of mathematics, but that was towards in terms of matrices. So nowadays whatever we are using for quantum computing is related to whatever Heisenberg has given. So that is related to mechanics part. And also he has famously given this uncertainty principle. And in 1932, von Neumann has given the mathematical foundations along with Paul Dirac. These two people have actually developed the overall mathematics required for quantum mechanics. So up to here, things were going very smooth. And there were obviously discrepancies, and even there was a series of debate between Einstein and Niels Bohr, especially in Copenhagen and all, and where they used to discuss a lot about the possibilities and the ideas of quantum mechanics. But in 1935, Einstein come up with a very unique, you can say he was a very good critic of quantum mechanics. So he came up with one question, and the question was related to something called quantum entanglement. So typically, if you, and which is very difficult to understand from classical perspective, that if you talk about two particles, obviously they will have their different states in terms of classical mechanics also. But and if you go to the quantum part, there can be two segregated quantum particles having separate quantum states, but there is a possibility that two separate quantum particles can have same quantum state, and that is a very not same quantum state. Actually, you can define one quantum state for them. And the reason behind that, these two quantum particles are actually entangled to each other. So the moment you are, and they can be physically separated. For example, they need not to be uh, in very close premises of each other. They can be really far apart. And in that case also, if you are aware of the state of one particle, let's say particle A, then immediately the particle B quantum states will be collapsed, and you will be able to find out the other particle state. So that is a very unique thing, and Einstein called it as a spooky action. And I think famously he told that God doesn't play dice. And so that was one major breakthrough happened, and that was the founding stone of, I would say, the application part of quantum computing. And so to provide a solution to that, even during Einstein time also, he expired in 1955. So by that time also nobody came up with the solution. And the first solution was given by John Bell in 1964, where he come up with something called Bell's theorem, where he actually demonstrated. It was theoretically predicted in 1970. The actual demonstration came, and for that, last year and last to last year also, Nobel prizes has been given. Uh, so that was the major breakthrough which happened in 1964 and 1970. So that's how quantum computing actually started. Okay, and especially after the talk given by Feynman, people uh, actually believe that yeah, it's possible to simulate things, or it is actually possible to realize or control the quantum behavior of the matter. So I would say one very basic diagram from here, that if we talk about the classical computer, these are again nothing but going to utilize voltage flow and this the current flow and uh, this the basic circuits and basic gates, and they are manipulating the overall information. Okay, and in the starting time in late 1940s, the computer used to be look like this, almost a room size big, and now we have very handy on computers, right? And if you talk about the quantum computers, nowadays we have really big size quantum computers, various sections, various units are there. This we will discuss also, and ultimately we are aiming towards realizing some handy quantum computers, though it will take time. Now we'll talk about the basic difference between quantum computing and classical computing. Some of the things you definitely will be aware of or might have come across in this particular workshop. So if you talk about classical and quantum, qubit part again I'll discuss, but just assume one thing. There is something called quantum bit, which is also abbreviated as qubit in case of quantum computing, and bit is there in case of classical computing. So in case of classical computing, generally we store information either SRAM or DRAM, especially utilizing transistors, and where we are representing them either in terms of 0 or 1. And that is the founding stone of Boolean logic. While in case of in quantum computer, things are a little different in a way that they are utilizing something called superposition. So the state of the qubit, or whatever the physical entity we are using to represent the information, can be either 0 or 1 or some in between. So in between, in the sense, some probability of, because we till we are observing, we will not be able to actually state the state of the system, or the quantum whatever particle we are having. So that's why we are always representing them in terms of probabilistic distribution function. So that is the reason. So it can be, and the same time it can be 0 or 1 or in between also. That is a very unique thing, not easy to digest if you talk in terms of classical way of understanding the information which is being stored. Second important thing is, if you talk about, say, power consumption. So if you are keep on increasing the number of transistors, similarly power consumption is also going to increase. That is going to have a linear relation. While in case of sorry, so computation power, while in case of quantum, if you are keep on increasing the number of qubits, the computation power is exponentially going to increase. So that is a major change in case of quantum computers, that just by adding one more number of qubit, you'll be able to exponentially increase the computation power. While in case of classical computing, it is going to follow an almost linear relation with respect to number of transistors. So this is also a reason why people are moving towards quantum computing. Then third important point is, which is typically a drawback, but if we talk about classical computers, so error rates are very less. And we have almost a variety of tools, techniques through which we can send almost error-free data. And we know that we can easily operate classical computers at room temperature. But if we talk about quantum computer, error rates are very high. And the error rates are very high because of measurement system. Okay, so quantum measurement also we'll talk about. So measurement itself can create certain level of errors, and that's why error rates are very high. And that's the reason why we have to keep them at ultra cold temperatures, typically in the range of millikelvins. So that is the reason, because error rates are very high, so we have to keep them at very low temperatures. Okay, and but good thing is, classical computers, obviously it is suitable for almost everyday processing. Okay. And even with the help of supercomputers, we can go for much advanced calculations also. But if we talk about certain operations, for example, optimization problems, or say data analysis or simulations, some complex simulations, not typical simulations. For example, prime number factoring. If you go to very high values of some prime numbers, and then you want to find out the factors and all, with classical computers it will become very difficult. But theoretically, quantum computers can easily provide the solutions, especially for drug designing, for weather forecasting. So all sorts of things can be easily handled with the help of quantum computers. Now, now we'll talk about the evolution of quantum technology part. Till now, we have discussed about the fundamentals of quantum mechanics, I would say. Now we'll talk about why or how we can approach towards quantum technology and how things have actually evolved. So I already told you the mechanics part, or the overall mathematics came in 1925 to 1935. That time, actually, Schrödinger, Dirac, Heisenberg, and von Neumann, they all have developed the mechanism and the language of quantum, I would say. And then the major question, or the challenging question, which was asked by Einstein, was EPR paradox. Then he was like, say, what Einstein was saying. For example, you are having a pair of gloves. So in his opinion, he told that it is already sorted. Like, for example, even you want to make two particles entangled, so automatically one will be having, say, left hand glove kind of appearance, and the other particle B will have a right hand glove kind of appearance. So even if you are keeping them far apart, means theoretically it is said that even they are separated by or beyond the reach of the time taken by light to traverse, still you'll be able to identify. So Einstein has predicted that, because they are initial, means at the time of generation itself, they are segregated in a way that one will appear as like, say, left hand glove, and other will appear as a right hand glove. So it is very easy to identify. But Bohr was definitely having different opinion. He was saying that no, it's a very different. It's not as simple as you are saying. These are entangled, and the moment you are exploring the first, then only the other particle will reveal its behavior. So it can be left hand, means particle A can be left hand glove or right hand glove property. Then automatically the particle B will show its behavior. Which was demonstrated in 1970 during that time. And after this famous lecture by Feynman, IBM started, definitely, and they started this quantum cryptography and theoretically how it is possible. And then Peter Schur, he came up with the algorithm, the first algorithm, almost not, it was not the first. Before that, Dewey's algorithm was also given, but during that time, means between 1984 to this time only, many algorithms came. Okay, Dewey's algorithm was there, Schur's algorithm was there. Even one of the Indian scientists, Love Gruber, he gave Gruber's algorithm for database search. And first working 2-bit quantum computer was demonstrated in 1998. So that was the first experimental demonstration of a qubit based quantum computer. And now we see how fastly things have evolved. Then this photon entanglement has been demonstrated. Okay, where D-Wave have come up with commercially available quantum computers, especially in 2010. So after 2010, actually major breakthrough happened, where variety of startups, variety of companies came into the picture. Okay, And now we are moving towards something called quantum supremacy, which has been claimed by Google, that with the help of quantum computers, will actually be able to decode most of the information, which is very difficult to do with the help of classical computers. And that's why it has become a rat race where almost every country and everybody is trying to link up. Yeah, but that's a good thing. Now, that's how we can clearly see the overall theoretical evolution. So theoretical foundations were up to 1980. Then the emergence happened up to 1994. And then the development is started from 1994 to 2000. And then this now race has just already started. And a good thing that in India also people have at least recognized the importance of quantum computing, and government of India also supporting with the help of various hubs and all. So soon we'll be able to realize full-fledged quantum computers. Soon means may take 1 or 2 decades. And these are the companies which are actually investing in the development of quantum computers, ranging from HP to Intel, so Mitsubishi or and Toshiba, Google. Almost every big organization is interested to develop this quantum computer thing. So this already I have discussed with you that how things have actually started. So Dewey's algorithm was given. This was the first, I would say, algorithm was given by David Dewey in 1985. Okay, and the first prime number factoring has been demonstrated in 2001, where this IBM quantum computer has shown how to go for the factors of a prime number. But this is a very big problem. And nowadays people are able to show entanglement and such kind of behaviors for much larger particles rather than just qubits or something. Now they are able to do it for quantum dots or fullerenes or even nanotubes. So up to that level, people have already, or scientific community has already reached. Okay. So now we'll talk about the terminology of quantum, how to understand. And one good thing is, especially if you are interested to explore quantum computing and quantum technology, you need not to worry so much about the quantum mechanics part or the quantum physics part. Means that you need not to be well versed with Griffith, though we have to read definitely, but still we can manage if we know the language. So, and in the language part, we can clearly follow the language developed by Paul Dirac, and which is nothing but bracket notation, okay, or also known as Dirac notations, where he presented one thing that we can represent the quantum states actually in in uh, in terms of this ket notations or bracket notations actually. So here, for example, if you want to represent a quantum state, what you can do here with psi is usually represented, usually followed to represent quantum states. So a line and then psi and angular bracket. That's how we can utilize to represent a ket. Okay, and if you talk about, like, say, how to even, because if you talk in terms of uh, uh, in terms of Schrodinger's equations, then things are little difficult to follow. So that's why people are mostly following this matrix representations, or especially the representation developed by the Heisenberg. So that is one very interesting thing which we are supposed to follow. Now, if you are going about the time evaluation, like for example, this is Schrodinger wave equation, nothing but in differential form. Del psi upon del t is nothing but minus I Hamiltonian, and Hamiltonian psi upon h cut. With Hamiltonian is nothing but one operator which will tell you about the total energy of the system, which is nothing but combination of potential energy plus kinetic energy of the system. Okay, so in classical mechanics, you can understand Hamiltonian is typically used to represent the total energy of the system. So that is one thing. Now we'll talk about why it is utilized. Like, say, what is the overall reason why we are going for this particular methodology? So the reason is because it is actually following the overall time evaluation of this quantum state. If you follow, it is following something called unitary operation or unitary transformation. So that is very good thing that almost matrix based or linear algebra concepts we can easily apply here, and we can we can simplify our things. So that is one thing. Second important point is, because this the overall observations which we are receiving in case of quantum experiments, these are probabilistic in nature. These are not deterministic, and so that's why again we need to write various probability distribution functions, and then which state is possible, and the probability distribution function of other possible states. In that kind of combinations we have to write. So good thing is the solution of Schrodinger wave equations are going to be linear in nature. So as these are going to be linear in nature, um, one good thing is we can represent the solutions in form of linear combinations of, like say, one solution. The overall solution we can write in terms of linear combination of basic solutions. Okay, so that is one very interesting thing which is happening, and typically means that it is going to follow superposition principle. So, and that is the reason why we are moving towards uh, this bracket notations. So now I'll give little more overview about this bracket notation. Okay, so if you can see here for this bracket notation, firstly I will talk about the ket, and then we'll talk about the bra. So ket is nothing but, for example, you want to represent some quantum state, or you want to represent, for example, a vector. Okay, obviously in vector space. Here we are going to mostly follow something called Hilbert space. So all this means this whole mathematics is defined under something called Hilbert space. Okay, which is nothing but a combination of you can say inner product space. So that we are typically using. Now, if you are trying to represent a ket, so ket is nothing but in this particular format we can show, where whatever function we are writing, the initial thing will be a vertical bar, and finally there we are going to put one angular bracket. We are closing it. We are going to close it by an angular bracket. So that's how we are typically representing a ket. Okay, and ket is nothing complicated. It is nothing but a column vector. Okay, ket is nothing but for whatever say basis vectors we can define. Okay, so the overall quantum state, if it is represented in terms of ket, will be nothing but linear combination of basis vectors, or we can also represent them in terms of column vector. Okay, so that's how we are typically representing a ket. And if you want to represent like say here itself you can see ket will be represented by a vector. So we can, this is nothing but a vector, a vertical line, and whatever vector we are writing, and angular bracket, and which is nothing but a column vector. Okay, so like say 1 can be represented as say 1 0 0. 2 we are writing it like say 0 1 0. I we are writing it as like 0 to so on up to I. Okay, and which will be nothing but linear combination of say x times the ket1, y times of ket2, and z times of ket3. That's how we are typically writing it. Now, if we talk about the bras, so these are again nothing but will be in the form of firstly angular bracket, then the function, and then vertical bar. Okay, and these are nothing but going to, or one way you can say that these are nothing but the complex conjugate of the ket. Okay, so if you are representing in terms of bras, then we are actually representing them. The complex conjugate, we are going to represent them in terms of row vector. Okay, so that's how we are typically representing. In direct notation, the bra vector will be nothing but angular bracket, the function, and we are going to close it by an vertical line, and it will be represented by the complex conjugate of the ket, and which will be nothing but a row vector. And if you are talking about the inner product, so that's the major thing. So typically for two functions f and g, we are representing the inner product like this: integration a to b and ft, and then this the complex conjugate of g t multiplied by dt, right? So this particular thing we are actually representing in direct notation like this. This will be nothing but inner product of vectors, which will be nothing but this multiplication of column vector, sorry, row vector to the column vector, right? That's how we are typically representing the you can say the quantum states in case of quantum terminology. So this is real mathematics part. Now we'll talk about how actually we are realizing what is the hardware part of quantum. Okay. So qubit, one thing we understood that it is nothing but a quantum bit. Okay, where which can have different states. Okay, and the states can be either 0 or 1 or some in a combination also. But we have to actually realize it, right? So the realization part can be done in a variety of things. One such thing is we can utilize the nuclear spin. Okay. Uh, so that can be identified in terms of in if you are applying nuclear magnetic resonance. Okay, in that terms, if it is up spin, then you can represent it by 0. If it is down spin, you can represent it by 1. You can also utilize photons if they are present in a cavity. Okay, so if 0 photon, then get 0, 1 photon, if get 1, like that. We can also talk about, we can represent the qubit in terms of energy states of atoms. For example, we know that various energy levels are there, like say 1s, 2s, 3s, and also and so on. And this is one thing. In case of molecules or in case of solids, also there can be various defect energy levels. Those can also be utilized to represent the states, whether it is 0 or 1. So ground states can be represented by 0, and excited states can be represented by 1. There is another physical technique through which we can represent the qubits. One is polarization of photons. So you know that photons can be left polarized or right polarized. Means a circularly polarized light can be differentiated into these two, and like say left one can be utilized to represent 0, so the right one will be utilized to represent 1. So these are some physical tools through which we can actually represent a qubit. For example, here we have already seen that variety of companies are there. So and they are putting bet on and so many types of qubits. Okay, for example, Google, IBM, and Rigetti and D-Wave, they are mostly focusing on superconducting qubits, especially charge and flux qubits. Honeywell and IonQ, they are focusing on trapped ion-based qubits. Intel, HRL, they are focusing on quantum dots-based qubits. And say Microsoft and recently many companies have started focusing on topological qubits also. So superconducting qubits are nothing but trying to make something called Josephson junction, which is like say for example, I hope most of you will be aware of PN junction, semiconductor based PN junction. So similarly, if you are making superconducting based junction, a junction between two different superconductors, that will be a Josephson junction. So that thing can be utilized to represent qubits. So based on whether Cooper pairs are forming or not, and I mean, so many things are there, especially. And these are also being utilized not only for representing a qubit. Superconductors also becoming important to make the wiring of the quantum computers. So, like for example, granular aluminum is there, boron dope diamond is there. These kind of systems are utilized to make the qubit itself, B, the circuitry part. Then trapped ions are also important. For example, you can trap cesium ions in some optical field, and then based on the energy states, whether it is in ground state or excited state, you can represent the information of various qubits. We can also utilize quantum dots, and we can create certain kind of defects in that, and we can expose it to microwave, and again we can utilize those splittings, especially in the presence of microwaves. We'll be able to actually probe. I would say, I hope we all know about quantum states, right? As a principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So magnetic quantum numbers can be utilized to store the information. Similarly, topological state of matters can also be utilized to store the qubit. Okay, especially nowadays they are talking about topoelectrical circuits and so on for developing such kind of things. So qubit, which I have already discussed with you, that it is nothing but uh, solutions of Schrodinger wave equations. Okay, sorry, the states actually. So these are nothing but going to be a way in which we are going to represent the information or going to represent the state of the quantum particle. So it can be either 0 or it can be means it can be ket 0, ket 1, or the superposition. So in order to clearly mention what we are doing, we are representing them in the superposition form itself. For example, if if you are using 1 qubit, it can have 0 or it can have 1. So that's why we are assigning some probability amplitudes to each one. Okay, so for example, for ket 0, we are putting alpha naught, and for ket 1, we are putting alpha 1. Okay, and alpha naught and alpha 1 are actually complex numbers. And we are
காம்பவுண்ட்ல வந்து பெரிய வழியா போட்டு அந்த வீட்டுக்கு வந்து அங்க இது பண்ணி இந்த வீடு வந்து சைடுல இருக்கும், புரியுதா? இந்த சைடுல இருந்து இது ஒரு வீடு இது மாதிரி இந்த அது வாடகை விடுவாங்க. வாடகை இதுக்கு வேணா மாடி கட்டுவாங்க. மாடி மாடி சரி பண்றது எப்படி ஹீட் பண்றதுல இல்ல அத கலை எடுப்பாங்க. கலை எல்லாம் ஊர்ல இல்ல சொத்து
Hello.
பின்னாடி வீட வேணும். அந்த வீடே இது பண்ணுவோம்.
Please mute your.
ஒண்ணு உங்களை டிஸ்கரேஜ் பண்றேன்.
Okay, madam. Yeah, I think some disturbance.
Okay.
So yeah, so one thing we can understand from here that these alpha naught and alpha 1, which we are defining as probability amplitudes, they are going to follow a unique relation that is called as normalization condition. So alpha naught is square, the mod of alpha naught is square, and mod of alpha 1 square should be equal to 1. So one good thing is we need not to do measurements separately for alpha naught and alpha 1. We can just do the measurement for alpha naught, and automatically we can find the probability amplitude for ket 1. Okay, so that's how we can find out which state is going to be revealed once we are going to probe it. And to understand that, we are utilizing something called as Bloch sphere, okay, which is nothing but you can say a mathematical representation where we are actually representing like said the various states of which are possible for a quantum system, whether it's a 2-qubit system or 3-qubit system, all can be represented here. Okay, so it will become very easy for us to understand the meaning of qubits or the meaning of operations that we are going to apply with the help of Bloch sphere. I'll just show you this part. Yeah, so that's how we are typically talking about classical and quantum bit. Classical bit either 0 or 1. While in case of quantum bit or qubit, we can have this state qubit ket 0 or ket 1 or some in between. Okay, so that is a very unique thing which is there, and that is happening because of superposition. So if you talk about the basic difference between these two, so we know that classical bits can have two distinct states, 0 and 1, and they can be measured completely. So that's a good thing. In case of classical bit, the complete measurement is going to happen, and the measurement is not going to hamper the state of the system, which is a very big problem in case of quantum. Okay, so measurements are not going to change the state, and it can be easily copied and can be easily erased. While in case of quantum bits, it can be either in state 0 or in state 1 or linear combination of these two states. So that is one unique thing which is happening. And how to find out which state means which state are actually the particles or the quantum systems are in. So that will be with the help of this probability density function that we are going to find out. Okay, and major problem is the moment we are going to measure the state of a quantum system, the state of system is going to alter. So the measurement itself can cause some certain amount of error, and that is going to change the state of the qubit. It cannot be copied in the way that whatever information you want to share cannot be copied. So cloning will be a difficulty. The moment somebody wants to clone, then immediately the information will reach that the data has been theft. And it cannot be erased also. So these are few important things which are related to quantum bits. Now we'll talk about the advantages of qubits. So obviously one such advantage is if you are adding qubits, the increasing parts is or the storage capacity is going to increase exponentially. For example, if you want to double the power of a digital computer, you have to go from 32 bits to 64 bits, right? Already a few days back, this has been demonstrated where Vikram processor have been developed, right, by ISRO. So, but if you want to increase the power, then definitely you have to go from 32 bits to 64 bits. While in case of quantum, if you want to double the power of quantum computer, then you have to go for 32 qubits to 33 qubits for same thing. So that is one thing. Why it is happening? Because in this case of quantum computers, things are going to have superpositions. So mostly the computations are going to have this parallel processing. So massively parallel processing is happening. That's the reason why quantum computers are much more efficient. Okay, so here itself you can see a 64 quantum computer can operate in a space of 2 to the power 64 dimensions. So how many states, though we cannot realize everything physically. So this is theoretical. Okay, because say in case of 64-bit classical computer, it can perform 64-bit binary numbers at a time. But in case of quantum computer, this is theoretically, means 2 to the power 64 or 16 into 10 to the power 18 numbers of quantum states systems will be able to process. But physically, we cannot represent each one of them. So obviously, it will be lesser than that only. But yeah, very complex processes can be performed. Now we'll talk about how actually we can do. So what actually differentiates a conventional transistor or lasers from the quantum devices that we are talking about nowadays? So in case of lasers also we are having quantum behavior. In transistors are also nothing but applications of quantum mechanics. But still, we don't talk about superposition. We don't talk about entanglement. Laser, to some extent, we can talk about interference or coherence, but we generally don't talk about all these things. But in case of actual quantum systems, we have to talk about all these three major processes. Okay, now we'll try to understand these three basic things: what is superposition, what is entanglement, and what is interference. So I would say one thing, like say for example, if you want to understand a superposition is nothing but say there are two states. So some probability for state 1 and some probability for state 2. For example, there is a meeting happening for European countries, and they want to make some Euro processor, and the European countries I can define it as EU bits. So and they want to vote for variety of tasks. So, for example, there is a debate that whether they are going ahead with nuclear fuel or basic coal or the conventional energy systems. So, for example, if we talk about the situation of Germany or what they think, that they are in dilemma. Like say, yes, we can. We have to change the climate. We have to come out of this renewable energy or the conventional energy systems. Then obviously they are saying that the major problem is if you are going towards nuclear, then there can be some other challenges also. So that's why they are in dilemma. So the answer for Germany will be alpha naught times yes plus alpha 1 times no. So that's how we can simply define the position of Germany. Simply, if we talk about interference is a very clear thing. For example, France is saying that nuclear energy is carbon free. We'll definitely go ahead with that. And Germany is saying that no, nuclear waste is very detrimental to the environment. So this is called as interference. So they are having, so similar way quantum states can also have interference. So then it will be very difficult. Now, if we talk about entanglement is a very unique thing. Like for example, two or three nations are there. For example, Denmark, Sweden, and Finland. And then Finland is saying, okay, if Denmark is doing this, then we'll do. And similarly, Sweden is saying, no, if or Denmark is saying, if Sweden is doing, then only we'll do, or we are going ahead with that. So this kind of thing. So if you know the state of Denmark, then automatically you know the state of Sweden. That's how we are typically to find out the entanglement part. So firstly, I'll discuss about superposition in more technical way. So superposition is nothing but the representation of quantum states as a sum of two or more distinct possible states. Okay, so mathematically, what it going to do? It is nothing but solutions of Schrodinger wave equations for a given quantum system. Obviously, for every quantum system, we should be able to write Schrodinger equations. Though we'll not be able to find out solutions as easy as we are able to find out for a hydrogen system, but still there will be solutions, and the solutions are nothing but going to be linear combination of variety of solutions. Okay, so here itself you can see we are going to represent the superposition state as alpha naught of state of ket 0 plus alpha 1 of ket 1. And these are complex numbers, and they are going to follow this normalization condition. Okay. And good thing is the states can be 0 or 1 at the same time. Okay. For example, one basic example which has been given by Schrodinger in his thought experiment, that in a closed chamber he kept radioactive material as well as a poison. The moment the cat is consuming that poison, there is a probability of this decay of this radioactive material. So what quantum mechanics says, that till you are actually probing the state, like if you are actually trying to observe, then only things will reveal. So theoretically you cannot say no, cat has died. As per quantum mechanics, it's always said that the quantum state or the solution of this particular quantum problem will have some alpha naught probability of cat is alive. Okay. Plus sorry, and some alpha 1 probability of cat is dead. So alpha 1 naught and alpha 1 theoretically are going to be 1 upon root 2 and 1 upon root 2. The moment you are actually opening the box and you are seeing, then you'll find that okay, alpha naught has become 1, or alpha 1 has become 1. So that's how things are going to work. But till we are actually probing it, we don't know the actual state of the system. Now that's how the superposition will actually look like. Superposition will be nothing but overlay of different states which are possible. Okay, so we cannot clearly define, but we can find out the probabilities, and then we can talk about the possible solutions. Good thing is it is going to provide parallel arithmetic operations. It is going to have obviously exponential multiplications per qubit. Okay, and massive amount of data can be handled in a very limited amount of time. So that is one good thing with the superposition. Now we'll come to the another problem that is called as entanglement. So entanglement is nothing but for example, if there are pair or group of particles and if they are interacting, okay, and if they are sharing some special proximity, in that case we can define something as quantum entanglement. The entanglement is nothing but they are need not to be described by different kind of quantum states. With one quantum state we can define the behavior of both the things. Okay, so we can clearly see that this entanglement pair is nothing but the overall will be nothing but a single quantum system, and which will be nothing but the superposition of all the possible states. Okay, we at the time of entanglement we don't know what information, we don't have individual information for the particles, particle A and particle B. Okay, only one thing we are aware of, that if particle A is having a state, say for example X, so particle B is going to have the opposite state. So that is one good thing. But the moment you are probing or changing means you are trying to measure, means obviously it is going to change. So if you are aware of the state of particle A, instantaneously the particle B state will become revealed, and that is going to be consistent with quantum mechanical rules. Okay, so means that once the measurement is done at part A, automatically at part B your the outcome is going to be automatically appear. Okay, and that is one of the most little difficult to understand also, and grasp also, that it is not a very classical, very simple thing to understand that how things are so entangled and how things are so connected. So that is was a major change between quantum mechanics and classical mechanics, which already I told you that Einstein called it as a spooky action at distances. But I think recently IIT Delhi and SSPL has demonstrated this quantum entanglement. And at what level people have already gone beyond that, much beyond that. They have shown much larger particles also to be entangled. So here, for example, if they are trying to play a game, so there can be cheating. Okay, so whatever action Alice is doing, Bob is going to immediately replicate if they are entangled. Now we'll talk about something called decoherence. So coherence is very important property of quantum. We know that, like say light, laser, if you talk about laser and LED, so basic difference is in case of lasers, the photons are coherent with each other. Okay, some coherency is there, some level of coherency. While in case of LEDs, we don't have that level of coherency. Means they are not in the same phase. So each photon will have its own phase. While in case of laser, they will try to have at least as much as similar kind of phase possible. So that coherency is also playing very important role in case of a quantum. Major problem is like for example, some information is being transmitted. The moment it is getting perturbed by some magnetic field or electric field or some other disturbances, immediately the coherence of that particular information or the state will change. And the moment it is changed, then you will not be able to retrieve the information. Okay. For example, this quantum phase coherence is going on, but because of some disturbance, now decoherence happened. Then you don't know what information, what quantum state has been transmitted. So it is actually nothing but loss of information from obviously system to the environment. Environment means the moment the quantum states are getting clubbed with or um having some interaction with the existing environment, the information is going to be lost. And the major problem is why we are actually still not able to realize quantum computers and to full-fledged quantum computers, because of superposition and entanglement are very fragile states, extremely fragile states. And they are very much prone. That means they are sitting there just to have some decoherence into the system. Okay, they're just dying out to have or incorporate some level of decoherence. So maintaining coherence is a big challenge to realize a quantum computer. Okay, for example, here itself you can see that some obviously repeating patterns are there, and here disturbance happened, and after that you don't know what information has been transferred. So that is very problematic thing, especially for relation of quantum computers or quantum communication or sensing. And disturbances can be impurities present in the material. For example, you have realized a qubit in diamond with some nitrogen vacancies added into it, and there are other impurities or other defects, they can create this decoherence. There can be particles present into the system. There can be electromagnetic waves interference. There can be mechanical vibrations that can also destroy the decoherence, can cause decoherence, temperature fluctuations also. And that's the reason why there are certain kind of materials, like for example, diamond or HBN and similar kind of materials, people are actually looking some certain level of temperatures they are actually going through, and they are isolating the whole system so that quantum computers can be realized. Now we'll talk about how to measure, like for example, even you have developed systems, right? So you need to find out how to actually get the state of the system. So typically a quantum system should be perfectly isolated. Okay, or if it is perfectly isolated, it is going to maintain the coherency. But if that's the situation, you will not be able to find out the state of the system. You have to actually go and probe it. So the moment you are going to probe it means you are creating disturbance, and the moment you are creating disturbance means you are trying to incorporate some kind of decoherence. And once decoherence you are trying to add means you are trying to manipulate the state of the system. So that's a very big problem. So now we have to understand to what extent we can incorporate that decoherence that later we can retrieve it. For example, this is one example we can see. Now we know the state of this cat is psi. Now we are trying to probe with the help of quantum measurements. Now with the help of that, the moment we are trying to probe it, the state got changed. Okay, now the state will be psi r, the cat psi r you can see here. Okay, and this will be the variation, little variation, in which because of the measurement itself, it has happened. Now we are trying to use with some circuits or some other things like to retrieve that. So okay, so in that case, we are going to provide some reverse operation. Okay, so that whatever change has happened here should compensate it. So there will be very less probability that we'll be able to realize the actual state. Okay, so that's what we can see. The act of measurement actually distributes the quantum information which is present into the system. So that's the major problem. So now we'll talk about the further things, gates. Actually, what kind of gates are needed to realize a quantum system, especially for quantum circuits. So quantum gates are also called as quantum logic gates, and these are nothing but basic quantum circuits which are going to be operated on qubits. And if we talk about the mathematically, so physically we can realize certain things, and the gates that we are going to talk now are nothing but mathematical operations, some matrix operations that we are going to apply on the states which are possible, whether it's ket 0 or ket 1, and we'll see how the states are changing. Okay. So one good thing is, so in case of every gate, the overall structure of gate is realized in a way that they are going to have unitary operations. Okay, so for every gate you will be able to find out that U cross U star is going to be an identity matrix. So that's a very good thing, and that's why, for example, if you talk about a classical gate, for example, I'm saying that the the output of AND gate, say, is 0, right? So if you know the output, can we tell what kind of input combinations we have used at the input end? We cannot say, right? In case of classical, for example, if output is 0, in case of AND gate, A can be 1 or B can be 0. Both can be 0, or say A can be 0 and B can be 1, right? All three possibilities are there. But in case of quantum computing, gates are designed in a way that based on the output, you can immediately trace down what kind of input combinations have been applied. Okay, so that's what I told you, that they are going to follow this basic unitary matrix operations. Okay, unitary transformations they are going to follow. So now we'll talk about individual gates first. What kind of gates are there? So for example, there is something called Pauli X gate. X gate is nothing but it's kind of you can say analogy of NOT gate that we typically use in case of digital. Okay, so for example, if your state is 0 and you want to flip it, so this is just want to change. This is a mathematical way. From 0 to 1, if you want to go, you can allow it to pass through something called X gate. So Pauli X gate is nothing but a mathematical representation. So if your state is 0, okay, ket 0, and you want to change it to ket 1, how to do it? There are two things. Experimentally, what you are going to do, for example, if ket 0 is nothing but the spin which is directing towards upward, and you want to change it towards downwards, you have to apply certain magnetic field or something so that it can be reversed from up spin to down spin. But mathematically, how will you understand? It is nothing but multiplying the existing state by matrix 0, 1 and 1, 0. Okay, so if ket 0 means it's nothing but a column vector having 1 for 0 and 0 for 1, means you can write it as alpha 0 1 plus alpha 1 0, where alpha 1 is going to be 0, right? So if you are applying Pauli X gate operation over that, what you are going to actually do, theoretically, you are going to apply one matrix operation. Okay, and the matrix operation X gate means you can represent it by 0, 1, 1, 0. This is the mathematical. And then if you are multiplying it, okay, what you are going to have? 0, 1. So means this can be represented as alpha naught ket 0 plus alpha 1 ket 1, where in this case, this particular thing is going to be alpha naught is going to be 0. So alpha 1 is going to be 1. So it is the earlier what qubit we have taken, it was having ket 0 state. Now it got reversed to ket 1 state. Similarly, if you are trying with ket 1 state, you are applying with this particular matrix, you will find that this got changed to 0. So this particular gate is actually flipping the positions of the qubits from 0 to 1 or 1 to 0. Mathematically, it is nothing but an operation where the matrix operation where you're going to multiply the existing qubits, existing states by 0, 1 and 1, 0 matrix, a square matrix. Experimentally, how are we doing? We are simply flipping. Okay, like say for example, you can change from left hand polarized light to right hand polarized, or spin up to spin down, some such kind of thing we can do. Similarly, you can use another thing which is very interesting, that is called Pauli Y gate, where you are going to introduce the imaginary part into the system. Okay, so imaginary part and even Pauli Z gate also. So these things are nothing but to introduce phases into the system. Okay, and losses also. So Pauli Y gate we can use, instead of 0, 1 and 1, 0, we are going to multiply it by 0 minus I and 0. Similarly, for Pauli Z gate, where you are going to multiply it by 1, 0 and 0 and minus 1. You can also go for S gate, or where you are going to multiply it by 1, 0 and 0 I. You can also call something as pi by 8 gate, where you are going to actually multiply it by 1, 0, 0 e to the power I pi by upon 4. So these are going to provide nothing but phases and going to introduce imaginary parts. Okay, so that's what we are seeing. These are nothing but mathematical operations. Then there is another interesting gate that is called as Hadamard gate. Okay, which will talk about some superposition thing. Till now we have output is nothing but just one state, while in case of Hadamard gate, we are going to have a superposition state. For example, if the existing state is get 0, what you can do, you can apply Hadamard gate. Hadamard gate is nothing but a unitary matrix operation where you are going to multiply it by 1 upon root 2, 1, 1, and the matrix elements are 1, 1, and 1 and minus 1. Okay, this is represented by this capital H, Hadamard gate. And once you are applying that, these states you are going to have. If 1 can be 1 by root 2 ket 0 minus ket 1, here it is going to be ket 0 plus ket 1. Okay, so these and how to experimentally realize, for example, like say here. So this is ket 0 and just downward is ket 1, but you want to keep it here, somewhere here at an angle of 45 degrees, for example, right? Somewhere here, if you want to keep the qubit position or the orientation or the rotation, right? So this particular operation can be realized by something called Hadamard gate. So experimentally, whatever things are possible, somehow we are trying to represent it by some mathematical operations. Okay, Hadamard gate is also very unique because it is going to have designed in a way that H is its own inverse. Okay, so that H square is nothing but an identity matrix. Okay, and this is nothing but one of the most important gates in case of computing operations. Okay, quantum computing. So now we'll talk about something called controlled NOT gate. So see, we have NOT gate, means Pauli X gate, but we can also have something called as controlled NOT gate. So because Pauli X gate, the moment you apply, automatically 0 will be converted to 1, 1 will be converted to 0. But for example, you have applied the gate, but you want to switch if a certain condition is followed. For example, you want, like say the control qubit, like say here there are 2 qubit. So if the control qubit, so 2 qubits are there. If the control qubit is 0, then target qubit is going to be the same. But if the control qubit is 1, then target qubit is going to be flipped. For example, if the control qubit is 0, then in that case, A is going to be same. But if the control qubit is 1, A is going to be flipped. For example, here itself you can see 0, 0 is going to be, like say 0 is the control qubit, then it is not going to change. Okay, like say 0 is the control qubit, 1 is going to be 1. But the moment control qubit is 1, the other qubit or the target qubit is going to be flipped. So this is called as controlled NOT gate or C NOT gate, which is kind of classical equivalent of XOR operation. Okay, so here you can see what are various types of gates are there: Pauli X gate, Y gate, Z gate, Hadamard gate, phase, the gates which are going to deduce certain level of phases, pi by 8 gate or T gate also, even control NOT gate, C NOT, CX gate, control Z gate also, swap gates where the flip, it can swap the positions of qubit 0 to 1, 1 to 0. So from this state, then we are also having something called CC NOT gate. Okay, that is also called as Toffoli gate. So these are certain unique gates which are there in case of quantum, which are very much different from classical gates. Okay, and good thing with quantum gates that based on the output, you can immediately trace down the what input combinations we have taken. So at least there you need not to worry about the error. Okay. Now, if you talk about the circuits, what kind of circuit operations we can realize? So a variety of things, like say any kind of circuit for parity generation, for communication, for like say for example development of quantum resistors, quantum counters, everything can be realized. Okay, with the help of this gate combinations. So here the example is taken from Qiskit, IBM Qiskit software, where you can define the existing quantum states and then you can pass individual qubits through combinations of gates, and then you can put some measurements also. Okay, so this will be nothing but for measurement. Okay, and then you can ultimately realize the output. Okay, so one important point is in case of quantum computers, like say in contrary to classical circuits, here we are going to have same number of wires which are going through the circuit. Okay, and the wiring is actually done with the experimentally the wiring is being done with the help of superconductors. Okay, so that's how we can realize, say for example, if you want to represent the Bell state, so what you can do, you can firstly apply Hadamard gate and then you can apply a C NOT gate. Then you will find that the overall the output is nothing but a Bell state combination of input states. Okay, means these two are nothing but entangled states. Two entangled states can be generated by this particular combination. So these are some of the things, and then I'll talk about the experimental realization. Okay. So now if you talk about quantum computer, like how actually a quantum computer will look like. So this figure already somebody might have definitely shown it to you. So there are various segments which are there for a quantum computer. The topmost portion we are actually keeping at a room temperature, and the bottommost portion is actually your quantum substrate, where you are going to actually keep your qubit, which can be a superconducting qubit, which can be a photonic qubit, or which can be trapped and whatsoever. And generally it is being kept at millikelvin temperature. So 20 millikelvin, they have kept it already. You can see. Just a minute. Yeah. So 20 millikelvin, you can clearly see. So to maintain that temperature is also not easy. It's very difficult. So that's why very few places in world these kind of facilities are there. And then to provide the connection, like say, to control the system, we need superconducting high density superconducting wires. Okay. So for that, we are using boron doped diamond or granular aluminum. And good thing is these things can also be simulated. Means theoretical simulations are also possible for developing these kind of systems also, not only for qubit. There are enough possibility to explore all these things also. And then there are control computers and memory hierarchy, which will be typically kept at liquid helium temperature. And then low density metal interconnects will be there, which will be generally kept at 77 Kelvin. And then finally, it can be connected to some computers. Okay, so that's how typically quantum computers are realized. And then if you talk about the design, like for example, why there are variety of things, right? So we'll talk about it now. If you see the requirements which are there to design a quantum computer. So first thing is to design a qubit, how to implement it, how to control this unitary evaluation. So to follow that unitary matrix operations, how to find out the initial state, how to prepare that, how to do the measurement. Okay. Then there are variety of problems, challenges. For example, you have to completely isolate the system from the environment. Okay. And you have to preserve the coherent systems, coherent states which are there. Okay. Decoherence time has to be very long. Okay. So that is also one challenge. So if the decoherence time is very long, then at least you'll be able to manage. Okay. And we should be able to perform a variety of operations on several qubits at a time, parallelly. Okay. Experimentally. And then ultimately to realize quantum gates and to entangle two qubits and all. These are some major challenges. Now, how to implement it? For example, here itself, you can see there can be liquid NMR, liquid state NMR kind of thing, or NMR spin lattice based systems, or linear ion trap spectroscopies are there. So variety of systems are there. Only thing is, some systems can provide you good control and configurability, and some systems are based on how many number of particles or how many number of qubits can be associated. So for example, if we talk about trapped ions and all, number of particles are going to be less, but control will be much better. And if you're talking about neutral atoms or quantum dots, you can have more number of particles, but control and configurability are going to be compromised. So that's why people are, for certain applications, they are talking about superconducting qubits, and for certain applications, they are talking about defect-based qubits, or they are even trying to connect one from this side and one from this side, based on a particular level of what kind of applications we are actually trying to explore. For example, if we talk about trapped atomic ions, so here itself you can see individual atoms will be trapped in a photonic field, okay, an electromagnetic field, and with the help of optical modulation, we can tune the states, either ket 0, ket 1, or the superpositions or entanglement. All sorts of things can be performed here. There are salient features also. So for these kind of systems, the memory will be like very long, like say more than 1 second. Means till that time, at least it will not have this decoherence effect. You can demonstrate it for say for 5 to 20 qubits. Okay. And atomic qubits are going to be all identical. Okay, connections are going to be reconfigurable. Challenges are like say because you are going to probe with lasers and optics to develop that kind of lasing units or optical units, that is going to be a big challenge. You have to go for very low temperature as well as to can maintain this kind of very high vacuum conditions. So that is one challenge. If we talk about superconducting based qubits, so good thing is we can connect them with wires. So that's why most of the companies are actually interested in superconducting qubits, because at least they are suitable with VLSI or CMOS technology. So printable circuits or these things are possible. Major problem is memory is very poor in case of superconducting qubits, and you have to go to very low temperatures, for example up to millikelvin temperatures only. Okay, and reconfigurability is also a problem. So that's why some, like say if you talk about NV centers and such kind of things, like say defect based qubits, so people are trying to club, okay, so that actual quantum computer can be realized. For example, if you want to realize a quantum computer, it should actually have this region, it should fall into this region, okay, for full quantum computer. So the number of qubits should be at least much higher than 10 to the power 4, and the error rate should be much lesser than 10 to the power -3 -2, and error correction gain should be at least much lesser than higher than 10. So these are some of the things, and we are actually up to here. If you see, we are actually at 1 or 2 position only. So to actually realize a quantum computer, it's a long way to go. So these are some of the things. And if we talk about the application part, so quantum computers can be utilized for obviously for the things which are very difficult for classical computers, especially for travel and logistics, and for game theory, for chemistry, especially for drug designing and analyzing biomolecules or DNA molecules and all, for discovering variety of drugs, for climate modeling, for financial analysis, especially for stock market, and for cryptography. So a variety of things are there for this quantum systems. So with this, I would like to conclude. If you are having any questions or anything, you please ask. Any questions from anyone? Yeah, can we use these circuits for classifications? Can be little more precise? I'm still not able to follow the question. Can we use these circuits for classification? What kind of classifications? Oh, classification. Okay, for machine learning kind of thing, or yes, okay. Yes, definitely. For quantum machine learning, also people are. I think one of my colleague, Dr. Priyanka, might have taken that session where they are focusing on quantum machine learning aspect. I'm not into that mode. I'm experimentalist, so I'm focusing more on the fabrication part. But yeah, definitely people are utilizing these things for quantum machine learning also, and for variety of classifications. And that option is there. I think in Qiskit or even in Pennylen, you can definitely try. Funding opportunities, I would suggest to focus on where electrical engineers actually can contribute towards the development of quantum circuits, especially superconducting circuits, and like say found up to club conventional devices, for example, transistors, and then try to incorporate quantum behavior into that, like say to control the spin behavior of electrons. So those kind of areas we can definitely contribute. Or if somebody is into semiconducting materials or devices, then a lot of opportunities are there to create, to find out a specific kind of defects, to develop that kind of defect, so that this coherence can be maintained. For example, we are working on NV centers in diamond. So how to develop that, and a variety of things are there, especially for single photon emissions and single photon detection. So those areas also we can explore. If original bits are modified in quantum cyber security, then how can we reach original bits? So yeah, that's why. So up to what extent the measurement system is affecting the information? For example, if the decoherence is beyond a point, then you cannot retrieve. But if it is within a particular limit, that's what we are seeing. So then we'll be able to retrieve. the information. For that, if you are interested, you can generally follow this very nice paper. I think this thing can be shared also. Where I've just kept it. Where I'm talking about decoherence. Please, you can just read this very good paper where they're talking about how coherence and all those things are being maintained in quantum systems. If you're interested, you can definitely read this one. Best textbook. See, it will take time. Like for example, even you'll be seeing that there was a trend since 2018, 29 to 19 about AI and ML. So I'm an old school guy. Firstly, I'll brush up my quantum mechanics principles by say Griffith book or Zetley book, or even I'm following Dirac book. Then you can go towards quantum computing part. Best book is Nelson. Nelson is really good book for exploring quantum computing, and then variety of things. Means quantum technology also. There are certain books. So. It will take time. If anyone is interested, definitely it will take two years to understand that. That at least minimum this much it will take. At least for me, it took more than 3 years. So still I'm like learning like anything.
So they're asking for the link of the paper which you mentioned just now in the
Paper,
chat
ma'am. Then
box.
I currently I'm not having. I'll share that. I'll share it with you.
Okay, okay, sir.
Mm.
So thank you so much, sir, that we have provided your time during the weekend to spend with the participants, share the informative session. We have got a lot of positive feedbacks regarding your session in the chat box too, sir. So,
Thank you so much.
from our participants, on behalf of the participants, I extend my heartfelt gratitude to you for accepting to come to this FDP, ATAL sponsored FDP. Yeah, in spite of your busy schedule, you have spent so much of time with us. Hoping to collaborate with you in the future also, and also invite
Definitely,
the
ma'am.
participants to interact with sir and make use of the information that he has given to us and take the work and the research forward. Thank you so much, sir.
Thank you so much, ma'am. Thank you so much for having me here. Thank you.
Okay.
Thanks
So
to
the
everyone.
next speaker is online. So let us welcome Kumar Gautam. Sir, are you connected?
Good evening.
You, sir?
Yeah, my voice is audible.
Yes, it is clear, sir. And
Yeah, good.
can we try just sharing the slide once? So just to check whether the
Sure, sure.
slides are also visible. Yes.
Uh, the share part is disabled. Kindly just allow me.
Okay, okay. Sir, can you rejoin once, also, so that you will when you join it will be as a host.
Okay, okay.
Yes, sir. Yes.
It's again the same problem.
So 1 second. So now it is proper, sir. You can try sharing the screen.
Yeah.
Yes, sir. Perfect, sir. So I take this opportunity to welcome Dr. Kumar Gautam, the founder and the president of QRace and director of eGreen Quanta, a very famous entrepreneur and researcher with us today. I welcome Renuka to introduce our speaker for this last session of the FDP.
Good evening, everyone. For our final technical session today on navigating the future in the transport industry, quantum computing for efficient route optimization, we are delighted to welcome Dr. Kumar Gautam. Dr. Gautam is the founder and president of QRace and director of eGreen Quanta LLP. He currently holds a postdoctoral position at GIST South Korea, focusing on the quantum vehicle routing problem and earned his PhD from Delhi University in quantum gate design. With over 8 years of teaching experience, he is proficient in quantum computation and QSDE and serves as a regional mentor of change under the ATAL Innovation Mission. A senior member of IEEE and fellow of IETE, Dr. Gautam has published extensively, holds patents, and actively mentors young researchers while collaborating with industry and academia on cutting edge quantum technologies. Please join me in welcoming Dr. Kumar Gautam.
Thank you so much. Thank you so much. Give me a great opportunity. Thank you so much, Dr. Deepa ma'am, to giving a great opportunity to interact on the quantum technology, particularly what exactly today is a it's a very prone to work on the people are supposed to be working on the transport industry, and this is what exactly I'm also working on the transport side. And today I'm giving them one how to people to create or to build a quantum algorithm for the particular on transport sides. And also we have to discuss in transport and particularly which segments are and what are the challenges in Indian prospect and globally where you are supposed to be a stand on the transportations or on or algorithm side. So I'm right now I'm working on the maritime side. I mean, previously was I developed a quantum algorithm for routing problems for roadways, and like I was a postdoctoral, and at that research was the Hyundai ways. So first 2023, my first algorithm published on IEEE transaction side, and my second algorithm I gave to Hyundai because it was some contract between me and Hyundai, so I did not publish because of that reason. But yeah, it was tested on somehow is today also we have to discuss about what exactly I supposed to without any knowledge about the quantum algorithms to somehow to practical knowledge and how anybody can start using the quantum gate technology or quantum gate based model
So
for the
one
particular
second,
use
sir.
cases.
Sir, 1 second. Sir, the slide, can you, is it in full screen or it is, yeah, now it is
No,
fine.
no,
Yeah,
yeah, it's
thank
okay.
you.
Okay. So, so mainly, this talk is more concerned about the basics to higher stage. And if you don't have any knowledge about the quantum technology, quantum terminology, even also today you also connect with how to start and where to start supposed to be. But my concern is always to choose first industry. I mean, as a startup, as an entrepreneur, always if you are supposed to be wanted as a researcher or as a engineers or as a BTech holder or MTech holder, if you want to pursue a career in the quantum technology, first you have to choose where to apply and how to apply particularly. So the terminology, every terminology is very unique, and try to connect with the real time examples, like a quantum supposed to be. Many people are know about this quantum and all, but today I am giving you one example, and I'm always suggesting to one book is also, and previous talk I heard that Nelson and Chuang is always, I mean, that was also I'm studying, still I'm studying Nelson Chuang along with the many books also there, but I am suggesting to everyone to read Nelson and Chuang at least chapter 1 to 5 or 4 somehow. Is 5 is a quantum Fourier transform, but the basic, if you suppose, if already you know about this quantum and basic things, then you can jump into the 5 to 6 and 7 and somehow, but you don't know idea how to start and what is the linear algebra, how, what is the tensor product and classically, and difference between the quantum and all, to start with the Nelson and Chuang first. And the confusion is, we are engineers suppose, and obviously as an engineer prospect, what books are more important about this, particularly whether you use Griffith or Dirac or anything like that. But obviously these books are always, it's very a hardcore book, and you should be always to carry these books. And but more importantly, as an engineer, how you're supposed to be connect with this particular, the first terminology is a quantum particular. But before that, you have to understand about this year. I mean, I congratulate to Dr. Deepa ma'am to initiate this FDP, because this year is UN has declared the 100 year of the quantum. So if you are supposed to be initiating or organize any conference or FDP, you are a part of actually this journey also. So you are celebrating also here the 100 year of the quantum is particularly. So this is the one is the global side. Now coming to the Indian prospect, what is the mission is basically, and why should be important for this mission, and why we are supposed to be this to contribute under this quantum mission, and how we will do that, or where to supposed to be initiate, whether it be the computing, whether it be the communication, sensing or material, and it where to impact is, if suppose you build a quantum algorithm, where to apply is best basically, and what is the impact of that in globally. And last is the more important, who is the biggest stakeholder in this domain. And as you know that IBM is the biggest stakeholder right now particularly, and I will share some story also about this, the story behind the stakeholder particularly, not only the IBM, maybe other Microsoft, Intel, IonQ, Rigetti, D-Wave. There is now many startups, many big companies also. Now in India, officially almost 40 to 45 startup is recognized. They're working on the quantum side. But obviously, as per the National Quantum Missions, they selected some 8 startup. But this is the just initiative. This is just a journey. If you have to just connect with the people, we have to just connect with the any of the professors, academia, and a startup group to initiate that. Now see that this picture is very important. I've always connected. Left side, this is just like a quantum. It's a technology. It's not a technology. It's like a warfare. So where to apply and how to apply? I said that. So choose today. You have to choose today this left picture. Where you want to start? Like either you want to just connect with the cyber side, computing side, communication, radar, meteorology, sensing, anywhere. So today you have to choose. This is the use cases. And now I will explain where you are supposed. Suppose if you are choosing one use cases is communication. So what exactly in communication you will do? If you choose, suppose you are in cyber. So how you are supposed to build a protocol? So either it will be for the quantum attacks or the classically or somehow. But today I am just saying, because I am giving a talk on the transportation side. So my suggestion is to choose stick on the transportation side particularly. So there is a huge area you can apply, you can build like that, means huge demand also. The lack of manpower, we are also struggling as a startup, as a founder. The big struggling is from my side is to lacking of the expert or skilled manpower particularly. So we connect with the people. I started the internship program also because of that. From that internship, I am hiring the people and they're working with me. See, this picture is also more importantly, before I start this, see, till now, ever more than that, 55 billion is the number globally invested. And India is somehow is the 60 and somehow is the 6,000 crore. This is the one number, but more than that, India is already invested the money. So this is the right now the scenario, and this number is continuously increasing. It's not like that. And see this China. I mean, where the India is supposed to be 1.12 billion, probably if you are supposed to be number 1 billion or 1.21 billion, suppose the China is more than 15 billion and somehow is true. So it's two things, the pro and cons also. obviously some country are investing the huge money and all. And it's not about obviously the money is also important in this technology, because the costing is the all this the equipment cost somehow is very high. And other than that, opportunity is also creating, like a Qatar, South Korea. I was in South Korea, and still there is many opportunity in South Korea. If somebody are interested on the quantum machine learning, communication, ERP problems, there's a huge opportunity in the South Korea particularly. And this is the actual one of the thematic hub. Recently, you heard that IT Delhi has basically tested the 1 kilometer LOS first for the space communication, particularly. And right side, one of the thematic hub and head of the Professor Neil Bhavakar, he is also leading of the one thematic hub. And the most important thing is obviously it's a one quote, but if you want to pursue this technology, to adopt your Har Kaam Desh Ke Naam. It means if you are not passionate about your technology, if you are not passionate about your idea, or somehow you will not do some. This technology is very weird. This technology is not supposed to be like a classical computer in a lot. We are struggling. I almost 13 years completed my journey in quantum. I started my quantum in 2012, and today is 2025. But still, I'm struggling, and somehow is to learning and many things. So this is the one of the problem statement in the just it closed now. But I'm saying this: the government is now focused on this side. Now, coming to the my startup, right now my three goals. I'm working on the three goals. One is quantum control gate based on the QRL side. Second is the quantum channel, and third is it is already selected by the Indian Navy. And I am also looking up people who can connect with these three goals, and there is opportunity to honor. Now, this picture is very important, and this is the actual picture. If you this slide and next slide, if you connect with these two slides, the rest all the slide is very easy to understand what exactly I'm talking right now. So if you I said that the story is very important, so connect with the story. Why the UN had declared 2025 is 100 year of somehow is we have to celebrate. That means in 100 years before, in 1925, someone has started, or some of the scientists has started the pitching, or something is the based on the quantum, or what is exactly and all. And before that, not only this story is 125 years before. I mean, the first time 1900, the Planck was started. The is defining the quanta. Quantum is coming to the quanta, and then Einstein is basically described that what is the nature of the quanta, and it's like it's a packet, so it's a wave like a nature. And then many scientists came, de Broglie and all. But the year in 1925, I'm always mentioning Schrodinger. Why? Because this is very close to my because my PhD on the Schrodinger dynamics. So I always put the first picture is a Schrodinger. So as I said that the Schrodinger, Heisenberg, Dirac, Born, de Broglie, these five scientists are basically to come up with this, so defining the overall the quantum sum. Some of the scientists they define this the matrix mechanism, which is Heisenberg. Sometimes scientists or novelists they define the notation of this the state of the quantum system, that is the PM Dirac. Some of that define the state based on the potential, which is basically the Schrodinger. And one of the scientists, which is more importantly, that is a Born, they define the interpretation of the giving the statistical predictions of the all variables, which is basically the probabilistic behavior. So when the Born explaining about this nature or state of the probability based of the nature, then the overall the definition is come. And then I will tell you the definition, exact definition, what is the quantum today after this slide. So next, many scientists gave, but in 1982, the first time Feynman gave the idea to create the machine which is based on the law of quantum mechanics instead of the law of classical physics. And he proposed this idea in front of the IBM. When? In 1980 or somehow is in 1982 something. And at that time, I mean, obviously, right now, who is the biggest stakeholder? And this obviously IBM. And this guy actually the Feynman was the actually he proposed this in idea, and some contradictions happened at that time. But after that, in 85, 94, and 97, these 3 years is also very remarkable year when the first time that David Dutch is developed the idea, they gave the start the Turing machines, showing the quantum circuit as a universal. And the 1994, which is more importantly, if you want to build a quantum algorithm, the Peter Shor paper is very important. I'm always suggesting to read the Peter Shor paper. And that SOAR paper is also helping people who want to pursue as a protocols for the quantum cybersecurity side also. And in 1907, the Grover is basically developed the some complexity of the quantum search algorithm somehow is. And then year 2022 and 23, these 2 years is again very important when these three scientists got the Nobel Prize based on the experimentally they proven that the entangled photon pairs and establishing the violation of the Bell inequality. And if the time is there, I will show you also this statement, what is the Bell inequality, and we'll show you the hands-on. So for the 5 to 3 minutes, just additionally, I will take. And this 2023 is very important year. And also, when I proposed the idea, I proposed the submitted the projects to Indian Navy. And the idea is basically validated when the 2023 was basically got the Nobel Prize, the synthesis and discovery of the quantum dots. So one of my project is basically developing the quantum radar based on the quantum dots. So these are actually the chronology. You have to connect with this chronology, then you can jump into the next is what is quantum. Now coming to this slide is a very important slide. And if you connect with this slide only now you have to understand how the states, what is the unitary evolution, what is the measurement, what is the coherence, what is the decoherence, everything you have to connect only if you're connecting with this slide. So as an engineer, and I read one book, I always suggest to that Nelson joined, that when I joined as a PhD scholar, like in 2022, it was as an electrical engineer to jump into the quantum. It was very difficult for me to understand what is the quantum. Then I read somehow is some statement, and that connect with this entire statement into the mathematical formations. So they actually define that the quantum is a mathematical framework. Understood? So, and that mathematical framework described by wave function, and that wave function described by Schrodinger equation. This is the what exactly. And I started the writing, the based on the definition, I started the mathematical equation and to connect with the exact definition, what exactly. So this is the definition of the quantum, and that definition is given in the Nelson drawing also. You have to go and read that chapter 1 and read line by line to connect what every statement is was written in that book. Now, when I understand, okay, this is the quantum is a mathematical, something is a mathematical framework. It's not purely mathematics, it's not purely physics, but it's somehow is because quantum is a technology. So it's just connect with if it is technology, that means it's like some framework, and entire framework is basically operating by or defining by or controlling by something. And that whole the process is somebody had basically to explain what exactly the quantum system is on. And the second one is what is the process. I mean, suppose I'm just giving one example today. This my talk is the last talk. So before this talk, what exactly the Deepa ma'am said at 5 o'clock or 5:30, the Kumar Gautam will give a talk. So what in your mind after the immediate your talk, you are somehow is preparing your energy because you have already drained your energy. Now the next talk is on the quantum. So you started your preparation of your energy states. So when the quantum system, if you're asking what is how many postulate, every postulate is basically it's a process. If you connect with this process, means you have to build your quantum system, you have to define your quantum gates also, and you have to build a quantum algorithm. So, like same example, what before my talk, you all prepare your energy states. So the quantum system also, before the evolution, the every states, that is the first postulate. See that the state space, the preparation of the states, and that all the state are coherent initially. Okay, so we are right now, we are assuming that all my audience are right now coherently. Whatever I am giving the input, you are supposed to be connected with the 100% with my energy or somehow is my talk or my idea. Now, when you prepare your states, then you have to feed into the quantum system. But the feeding of the quantum system can understand the one technical terminology that is called Hamiltonian. And that Hamiltonian is nothing but it is called energy. Like in 10th or 10 plus 2 in childhood, we know that what is energy. Energy is the same kinetic plus potential. The same thing is happening here. And the Hamiltonian is nothing but it's a kinetic plus potentials. But when you are considering the kinetic plus potential, it is a unperturbed. There's some state are in the steady state mode. But when you're putting any disturbance or any force, then it started. Energy is basically started one position to another position, right? So that what exactly is the two operators? One is the potential, one another is a momentum. Kinetic is defined by the p square by 2m, and potential is basically just you have to consider the b. So based on that, the Schrodinger is basically why I'm putting the statement कि quantum is a mathematical framework. Mathematical framework described by wave function, and that wave function described by Schrodinger equation. Schrodinger said we are not bothering about the momentum. We are bothering about the only potentials. Okay. So now the next Hamiltonian, what exactly? It's based on the only potentials. The first Hamiltonian is H naught, which is combined with the kinetic plus potential, and next one is the just potential. When you prepare your energy, means Hamiltonian, then you have to feed into the quantum system. Now the second postulate said that after the evolution, whatever the input you are giving, suppose here we are giving the wave function psi, the output is always unitary. This is the ideal case. The quantum system is unitary. And why it is? Because we are basically creating the superposition state, right? Because all are the coherent. But practically it is not possible. Why we are struggling? Why the all big stakeholders still they are struggling to building the quantum computer? Because of that, this unitarity is violation. And how the unitarity is violation? They are interacting. This is very sensitive. Quantum system is like a baby. Okay, and so baby is very sensitive. They're interacting with the environment also. So quantum system is also interacting. When they're interacting with the environment, they lost the coherency. Okay, and this is the other many certain region also. But I'm just giving us very layman terms. So you have to maintain this. Second postulate is said that after the evolution, the output should be unitary. And the third postulate information is there, and it is based on the probability. And that I will show you also in the hands-on today, right? And one more postulate. I'm just explaining about the three postulate because for me, for quantum algorithm, we are just bothering about the three postulate. But total postulate is fourth, and the fourth one is the composite system. When the multiple quantum system are interacting at the same time or interacting each other. But right now, we are not supposed to be taking out the multiple quantum system. We are just whether you are supposed to be ion trap, superconductive, NB atom, NMR, quantum dots. You just pick one quantum system and start your work in this any of this supposed to be. Now, if you connect with this previous slide, now this slide is again very important. Why? I am just you know that the classical and quantum and everybody is explaining about that. But why I am putting this slide? I am sharing the problem statement, not about the only the difference or significant about the quantum computing and quantum classical computing. Today I am sharing two problem statement in that based on these classifications. So see the first is advantage. Quantum computer, obviously it's calculate the qubit is basically represented at the same time 0 and 1. It's a superposition. And in classical, you know that it's like a switch. It's at the same time, I mean, either 0 and 1. It's not like a quantum. So, because it's calculated the transistor. Sorry. Now, second, when you increase the number of qubits, when they increase the number of qubits, the power is increases. Now, this is the drawback exponentially. So your job is now today I'm sharing the one problem statement, everyone. Is it possible to build a low power dissipated quantum gate based on any of the interaction, whether it will be the electric, whether it be the magnetic, or whether it will be the electromagnetic? But in classically, the power increase the 1-to-1 ratio. It's like a linear. But in quantum side, this is the drawback. Okay. So your job is it possible to build a low power dissipated gate with the limited qubits? Okay. Because some of the application is feasible for the limited qubit. And it was published. One of my paper is published on the in IEEE. You can visit that paper where I applied with the limited qubits for transport industry. And that is one use cases you can fix on the qubits. And what is the actually the fixation or limited qubits that I will tell you the later slide. Third is again it's a drawback. And I am setting another problem statement based on the third significant. I mean, classical computer have a low error rate, and it can operate on the room temperature. But in quantum computer, it's a high error rate and need to be kept ultra cold. So Is it possible to build a fault tolerance with quantum computer? IBM is already declared they will launch and by 2035 FTQC based quantum computers, fault tolerance based quantum computer with a low error rate, right? So that is another problem statement. But I am suggesting to choose ion trap and start your reading, start your research on that particularly. And that problem statement is it possible to build a FTQC based ion trap with the low error rate with high fidelity? This is the problem statement based on this. And the last one is its advantages. What exactly I am talking right now? Because I will share the one live example. You have to just stick on that. The last one is, and because just 3 months before I visited to Kandlapur, and what I saw and what I faced the challenge and what we needed to build something in a different way to larger data, tackling the optimization and somehow is. So last one is if you're taking the n number, I mean millions of millions data, to use that quantum optimizer, because the quantum optimizer is basically it feasible with the both the case linear and non-linear. Right now, the whatever the optimizer is there and tackling there basically linear based programming, and even the OR tool is also it's based on the linear base. So many problem statement they are not supposed to be possible to build or to tackle this the classical. So now it's need to be build a quantum algorithm, whether it be the hybrid based or with it with the whether it will be the meta heuristic based. So my suggestion is to choose a meta heuristic like a QGSO, PSO, BHO. Just put the quantum inspired based BHO, quantum inspired based GSO also. And I will share you today the quantum inspired based gravitational search algorithm. So my slide, my talk is today to how to build a quantum meta heuristic optimizer for transport industry. So this is the significant and that. Now coming to this is very everyone familiar about this. This is the property basically. The three properties very important about that, and it's not only to understanding about this property to show this what exactly the meaning of the superpositions. Superposition means what exactly the system can be the two or more of the states simultaneously. See this picture, and the multiple states are at the same time they are connected with this one. So psi is equal to cat psi 0, cat psi 1, cat psi like, and at the same multiple states are connected at the linear form. And superposition is it's not a quantum terminology, it's a very basic mathematics terminology. Superposition follows the homogeneous as well as linearity. So this homogeneous and linearity, that means we studied during the school time. It's defined by the differential equation. So if you see this, the equation of the Schrodinger equations, first order, it's same like this differential equation. So somehow is I'm always saying that it's something is related to your school time to connect with the basic things to apply on this right now. Second one is a correlation. Obviously, it's every qubits are actually correlated each other. And third is the entangle. When see this picture, when it's entangle and break it, they're still entangled because whether it will be the northern pole or whether it will be the southern pole. So these three properties very important. If you connect with these three property, you can start your work and you can start your now the terminology. It's very important. What is the terminology? It's a single qubits. I mean the single qubits. Obviously, it's a two possible state, cat 0 and cat 1. And if you're representing the cat 0 and cat 1 in the form of matrix, right? This is the matrix. So it is called matrix mechanism. And who gave this matrix mechanism? Heisenberg. So Heisenberg, if you give this, if you represent all these states in the form of matrix, it is called matrix mechanism. So quantum mechanics is the matrix mechanism also. It's a second definition. And if you're taking this is the superposition set cat psi is equal to A cat psi B plus B cat psi. This is the simple, this is it's A and B as like a homogeneity, and this plus sign is a linearity. And if you're taking the norms of the A plus B, A square plus B square, and it should be unitary one, that means it is basically it must be the unit norm. And if you can just it's connect with this equation, what exactly mean? I said that previous slide, use this one. In the second postulate, after evolution, the quantum system gave unitary evolution. Why it's come? Because based on this equation, this. So always it should be unitary. If unitarity is violated, suppose you have to maintain the unitary using some techniques, and also, and we'll share to you how you, if it is violated the unitarity, how you are supposed to maintain the unitary also. So when this picture is come, when this equation is come, then it is called probabilistic, means total maximum probability should be, it's always a 1, means 50 plus 50% plus 50% is like that. And based on this equation, it is called probabilistic mechanism. So quantum mechanics is also probabilistic mechanism. Based on this equation, this representation, quantum mechanics is a matrix mechanism. And overall definition is a quantum is a mathematical framework describe a wave function, and that wave function describe a story. So these three definitions are overall based on the every statement and all. The coming to the last, that is more important. All the quantum operations have to be reversible, but Boolean operations are not supposed to be. And how unitarity matrix should be maintained when the reversible operation is occurs, right? So think about that. If Hadamard gate or control gate, if it is reversible, then it should be the quantum gate is supposed to be unitarity, right? And how you will check this unitarity matrix? So this is the basically the check whether it will be unitary or not. Just you have to take the U 2x2 matrix example, and U dagger is equal to, if it is like a unitary, means all the diagonal elements should be 1 and upper and lower triangle matrix should be 0. So this is the your, so if your quantum system, suppose you are building a 3 qubits Hadamard gate, and I'm suggesting to go my paper. Even my thesis is also in public archive. So in 2015, I developed a first 2 qubits Hadamard gate, and then after I developed a 3 qubit Hadamard gate. Then I developed a control gate, and also we build up protocols how to develop a control gate for 2 qubits and for 3 qubits also. Now, this diagram, again, I'm just going to back first. Just see this diagram: 1 state, 2nd evolution, 3rd measurement, right? Now coming to this. This is the control gate. Now the first is, if you now, the time should be understand how to write a mathematical form. So the first diagram is just nothing but it's a state. State means, initially I said that initially it is considered the H naught. H naught is nothing but it is a basically kinetic plus potential. And the next state is basically it's only potential. So how it occurs? You have to putting the small, how the ball rolls. If something is steady state, you are putting the external disturbance or putting the external force. And this epsilon is your disturbance. And the state are changed basically. So states change in the form of potentials. So initially the potential is suppose the E naught, the next is E1, next is E2, E3, E4. It's like a one-dimensional. And overall Hamiltonian is basically the H naught plus epsilon Vt. Now this is called agent. So if something is, who will carry your information? So in layman, this agent is, it's like a postman, right? And so what exactly the postman is actually is doing? Postman is carry your letters, and they will just send this, or through any channel, they send this information that later to one destination to another destination. The same thing, you have to, where you are putting your data or informations or anything, you have to modulate your data with this with this Vt, because initial the kinetic and potential both occurs. So if the next potential is basically your real agent to carry your data, and the same thing is the postman and letter not commute each other. This is the condition. No, postman cannot open your letter. The same thing, your data and Vt is not commute each other, because quantum operation can understand only Vt, not your data. So whatever your data is supposed to be, you just put here, modulate with the Vt, and then start your process. Now, first you have to build the Hamiltonian. Now the question is, sir, what is the Hamiltonian? And is the Hamiltonian nature is change or something? Yes, it will change. If you consider the quantum system is harmonic oscillator, the Hamiltonian is different. If you consider the Hamiltonian quantum system is a superconductivity, then Hamiltonian is different. How it's a different? Every system has the potential different. Like my potential is different, your potential is different. The same thing, the quantum. In the ion trap, potential is different. Superconductive, potential is different. and harmonic oscillator is the potential. So my concern is to first you have to choose which quantum system is supposed to be start your journey. So my suggestion is to start from the harmonic oscillator. Now harmonic oscillator potential is very simple, half m omega square x square. So now you have to put your potential here and prepare your Hamiltonian. Now once you prepare your Hamiltonian, now you have to fit into the quantum system. This is the first state. Now when you are feeding then start the process. And as I said, the second postulate is what exactly? It's maintain the unitarity. Now, after this output means this third blocks before that, you have to check whether this quantum system or quantum operation is unitary or not. If it is ideal, obviously it should be a unitary. But we are talking about the real-time use cases. And the real time, this quantum system is not unitary, right? Because of the interaction picture. Right. And what exactly when the some state are interact with the another state, it's definitely it's violated. So how you are supposed to maintain this? Now the journey, now the challenge started. Now I propose that in 2016, the idea is truncated Dyson series, first time, and maintaining this unitarity. How is supposed to be? You can also choose this idea. TDS techniques is very useful, and it is already tested by the real time. And I tested this applicability in the transport industry. Right, what exactly is? So you have to just nothing but this is a continuous domain, it's an infinite domain. You have to put one switch in between and truncate it, means infinite to finite first, means discretize. Then, so suppose here ut, now it's a time, u of big T, that is basically discretized unitary gate. Now you have to compare your ut, derived unitary to given unitary. And this given unitary is basically your ideal unitary gate, like all the diagonal elements should be 1 and upper and lower parameter should be 0. And you have to put your cost function. See, there is n number of cost function. My suggestion is to choose either spectral norms or Frobenius norm. I use the Frobenius norm cost function here to testing whether the get error energy should be minimum. If it is a minimum, suppose zeta mean is about to 0, that means the UG is approaches to or UT is approaches to UG. UG is 111. If your derived unitary gate is supposed to be 0.9, 0.89, 0.92, like that, all diagonal means job is done. And all the upper, obviously it's not purely 111. If you are going to the ideally, practically, then definitely it is very, but it should be close to the 1. Like if your one matrix, one number is 0.6, that means it's not perfectly 1. Right. So your number should be about 2.9, 0.89, 0.95. It's like that you are achieving this at all the diagonal elements, then your job is done basically. So this is the overall process particularly, and you can start your quantum gate operation in everywhere. So what is the uniqueness? What is exactly the change? If you are going to the ion trap, just you have to find out what is the potential of the ion trap and put in here the B you have to change, and the H is same H naught plus epsilon, the potential. If you are choosing the superconductivity, just you have to find what is the potential of the superconductivity. If you choose the quantum dots, just change the find out the potential of this and start the preparation, and that's all the process that's same like that. Now this is I am citing this paper. This is my 2015 and 2017 paper where I build protocols. You can also go and read that book, read that paper, and build the two-bit. Here I developed this the implementation of the control gate, the 3-qubit based, but I'm suggesting to start from the 2 qubits. 2 qubits means four possible 0, 0, 1, 0, 1, 1. 1, 0, and 1. This is like that. But it's like you can increase the n number of x1, x2, x3 to x of n. So you can build the n number of a control gate, n number of control gate based on the state. So this is the process, and I am right now. I'm also putting the control gate for the one of the application is the communication using the developing the trusted node, right? So if you are supposed to be build one of the control gate or one of the unitary gate and apply this control gate in any of this use application, whether it be the communication, whether it be the cyber security, whether it be the transport also. So here we are actually using the control gate to build this one. And this is the process. Very simple. It's very simple. How it's a control gate one. Suppose suppose it's a two qubits. Just consider the 2 qubits control gate. Like what exactly how the what is how it's worked in control gate? 1, 2. If the first qubit is 0, the next qubit is unchanged. If the first qubit is 1, the next qubit is it's basically changed. So how you are to build the control gate is building the control gate based on the what will be the first. So you can write your protocol based on your assumptions. So like that, if the control qubits is state 0, the target qubits is not. So next is the target qubits. The x1 is your control. So if I'm saying you have to put the if the write the protocols today, if x1 is 1, then the next target qubit will change. Either it will be the one x1 change or other it will be the both the change, like x2 x3. If it will be 0 0, then 1 1. So like that. So you have to write your protocols in the your way. You can write a protocols like no, I will not change the next qubit, I will change only first qubit or adjacent qubit, like that. So it depends on you. You can build a control gate based on your assumptions on you. So this is the just I'm saying this is the matrix or somehow is, and that detailed analysis is already given in my paper 2015 2017 paper. You can go and read that. If you have find any difficulties, please connect to me. So this is the overall journey. Now coming to this problem statement. So today we have to build like how to develop the protocols, and the quantum computer, how it's supposed to be build a quantum optimizer, like a quantum based optimizer or quantum control. But before that, what are the actually the parameters should be needed? Like you have data set also. Like I say I visited Kandla port. So we are planning to develop a quantum protocols or quantum algorithm for maritime. But what is the biggest drawback somehow is the Kandla port is basically they don't have a data set right now. So if they don't have a data set, how you are supposed to be build a quantum algorithm? Because if you don't have a data set, you have don't module data management module, you cannot apply. See this. So applying the heuristic protocols, first you have to build a protocols data management. So the people who are expert in the data management or data modules, we need a people who are supposed to be build a generated file, deported file, vehicle data, or picking data, everything interested. Second is obviously the technical part to who will working on this the simulation model or heuristic. Now we have to combine both the things into the application of the reports management. What exactly the routing management, and who will the somebody are controlling the entire, and this control module is basically tackling this both the data management as well as the your heuristic model. And then you have to apply into the, and this control is who is controlling in the quantum system. This H is controlling. I said no, the H is your agent. So H is basically carry your this information, and then you have to feed into the quantum system, and then quantum system is start your routing problem, and it's like that. This is the example of the vehicle routing problems, and you can work in this like this is the this idea. Now to coming to this, how you have to build the quantum algorithm. See the right side, it's the same like you have to just connect with the this diagram, this diagram. Again, you have to connect the agent, operation, cost function, and then the fourth one is optimizer. Now coming to this here, see how you have to convert all mathematical part into the optimizer. See, if you see this, if it's visible, the section one is nothing the same is the agent H naught and epsilon. Now we have to put the modulating the data. Whatever the data, whether with the maritime data, with the aviation, you need one data module. Now feed into data module with the modulate with the PD and prepare a Hamiltonian. Now here this Hamiltonian is basically it's a combined with your data module also. And now when you prepare your Hamiltonian, feed into the quantum system. Then have to check what is the output of the quantum system. Where it is unitary, it's okay. If it is not unitary, obviously practical, it's not unitary. Now first we have to maintain this unitarity condition. So section 3 is the same like that, but exactly the previous one. And check whether the quantum gate error is function is unitary or not. Yes. If it is unitary, then you have to apply your optimizer. I am showing this quantum gravitational search algorithm. GSO is basically it's working on the mass based. Larger the mass, if you have 5 nodes, 1, 2, 3, 4, 5, and check which nodes mass is that. If suppose the mass 2 for certain nodes the mass is larger, so the vehicle will go from the depot to first to 2003 and 5, it depends on the mass. So this is the basically the logic behind that. If you're at work, if you're supposed to choose the BHO side, black hole optimizer, so see, it is sorry, it is working on the star density. So every optimizer has own parameter, and sometimes I suggest you to choose the global minimum based optimizer like that BHO, GSO, GWO, and somehow is, and then start your working. So this is the overall process, and I am now bifurcating the each sections to how you have to build. Like as I said that first you have to build the data set to build the Hamiltonian. So you have to, this is the Hamiltonian process. Second, if you have prepared the Hamiltonian, then you have to check whether this unitary or second section, check the unitarity. Third, if it is not unitary, then you have to maintain the unitary of the comparison between the derived and given unitary gate. And the final one is to optimize this. So now you have to change this QGSO is QBHO, QWO, QGSA, GIA, anything, any optimizer. These are the metaheuristic optimizer, the process. And then this is the optimal data. And then automatically it's, so this is the diagram. What exactly? I use the three vehicles, and this red, green, and blue are basically it's a path of the all the three vehicles, and the red is the depot. So this the 10 city and how the vehicle are basically decided. So it's basically all three vehicle of the optimal path. This is the just some assumption for practical realizations. You have to also maintain this assumption should be needed. And if you want to build a quantum algorithm, so this assumption is very important to considering of your process. And last is because the first time I developed this NECR, noise to signal energy ratio, and see this how my NECR is about 2.07. I mean, it's almost zero. Like, so that means if you're supposed to be see, and goes to the almost 0.001. So this NECR is perfectly work, and I maintain the quantum unitary gate is it's about to somehow is a 111. My matrix is about 2.9, 0.99, 0.98, and somehow is. So have to just some assumption is very important, and you have to just skip this assumption and start your work on to building this quantum organized. So this is a just rating problem. This is the basic things how you are supposed to be maintained: minimum cost, minimum distance, and minimum traveling time also. So I am just sharing a small video here. You just connect, and if it is volume is okay, and and then I will. So what exactly the purpose is?
Sir, is there audio is not shared actually? Is there an audio for this?
Audio is not here.
No, no.
Okay, no problem. I will share and just simple. So what exactly is that? The how we are supposed to be the in shipping industry to optimize the shipping route, cost, enhance the sustainability, and using the quantum inspired solution. And this is the very and using the real data analysis. And what is the biggest challenge? See this. This is the biggest challenge right now. Inefficient in the, I visited in the cargo. I mean, if suppose the next visit is also very soon in the Goa port, and if anybody are supposed to be interested on this particular domain, I will also invite to visit, because if you are not visiting the real time scenario now, you can't work. In particularly in India, when in I visited in DHL, because it's a private and somehow is in South Korea, it's very organized way. But when I visited to somehow is, I'm not criticizing you right now, but I am just saying to connect with the problem statement, then you start your process and somehow. What exactly I found? Inefficient cargo loading optimization. And if it is inefficient, then definitely the high fuel consumption emission. See, India is supposed target to how supposed to be green the carbon credit or by 2030 to reaching 40%. See, almost 90% trading is depends on this, the shipping industry. And still there is an inaccurate storage planning, lead loading, increasing the operational cost, and difficult to handling the complex instituting the route. These are the main pinpoint, and you have to choose one of the pinpoint and start your work on it. And see this, what exactly, this is the actual diagram. I'm working on this. You can start. I visited total in Kanda port is, I'm just example, I'm saying, well, just take 1 minute. Total 12 vessel. Vessel is just like a platforms, like, and a one vessel is suppose, I mean, I'm not talking about the right now container based. This is like a tinder or coilas, anything like that, right? So you have to start your work from the vessel to, or don't go for the shipping routes. I mean, you have to start your yard optimization. You have to start from the vessel to yard, yard to gate assignment, and then gate assignment to somewhere. So this is the what exactly the process. There is a seven verticals: storage planner, loading planner. Means one quantum shifting is maintaining, is basically to optimizing all the seven verticals. Container to truck calling, cost, yard of right now. What exactly the government is more concerned with Kandla port? They said that we are more focused about the yard, and I will share your yard optimization part also to everyone. If anybody are interested to build in the quantum algorithm for the yard of just one container to truck calling from the yard to truck. And then last is the security. What exactly is it possible to build any of the quantum optimizer to tackling the both the side routing as well as security? That is another the case gate assignment. It means in Kandlapur this RFID is very, I mean, very old, and there is a many time it's mismatching of this. The means the sensor is no so much actually. So you have to also build a quantum sensor. You have to also build a something the RFID based quantum security for the gate assignment. If it is all the container are not fulfilling, you have to pick this. And the last is basically it's a consolidated system, that is the bin packaging. It was already tested or somehow is used by the Airbus into 2020. So this is basically. But my as per the when I discussed with the secretary of the Kandla port and all, he said my problem statement is to start your work on the on either vessel to yard, or just only you maintain the yard optimizations particularly. Now, I said that when I starting the yard optimizations, so how your classical to quantum overview is supposed to be. And see, this is the basically the technicality and global case is like a in outside the country like Germany, US, South Korea. There's many other efficacy, but still there is a big lacking. With they are also struggling on the quantum side, particularly there no till now no quantum algorithm are supposed to be applicable on the maritime side. This is the just the number challenges from inbound to outbound. Means you have to don't go for the routing problem for the country to country. You have to maintain the routing in the inside, so vessel to gate assignment. This is the basically I'm suggesting to start reading the metaristic. That is a more actually. See, the first algorithm. I mean, not talking about the global search. The company is D-Wave. They launch 2020 somehow is they launch QAO, a quantum annular, and they claim that this is my quantum optimizer. But after some year, 22 year or somehow is nearby, they said no, this is the hybrid based optimizer particularly. So then they start the preparation or they start the building on quantum computer for that algorithm. I mean, QA is not bad, but my suggestion is to, if you are choosing the quantum algorithm, to start your meta heuristic, start your work on the quantum inspired with meta heuristic, which is exactly the quantum PSO, GSO, BHO, GWO, anything like that. Swarm based, evolutionary based, or you have a three option. This is the three categories, and you can choose or you can pick any of the categories and start your work also. This is the basically the option. You can choose any of that and just put quantum inspired to like B colony, Grey Wolf, and on. And today here I am another example is one of my student. They are building this. They are basically build this on GWO, not for the maritime. They are working on the EVs, particularly the electric vehicle optimization, all for the how the vehicle will optimize the on the charging station, particularly the nearest charging station is very close to your home or somehow is. So this is the overview about how to understand the characteristic of this or understanding of the exploration for explorations. Basically, high adaptability is very important to understanding of the which metastatic optimization is whether it be the global minima or whether the local minima also. So why quantum knocking is particularly now the time should be very important to choose that any of this algorithm. And obviously it's somehow it's a very difficult to understand. It's very mathematical things. But my suggestion is to start something in the basic, and then you can apply for your quantum side. First, try to understand all the classical behavior to optimization the NP hard problems, and then you can apply for the quantum optimization for the NP hard also. So the key principle is, again, I said that the same thing: qubits, superposition, entanglement, parallelism, tunneling, internal. These are the key principle. And before that, you have to try to understand writing this or studying these things through any of the paper, any of the book. And I already shared, and previous the speaker also said that the Nelson Chang is a good book for that particularly. So you can start your reading with Nelson Chang. That is a sufficient. And if you want to more, you can just choose my paper also. That is also very basic things, and my thesis already in public and archive. So this is the potential. What exactly is the space explorations? This is another. The key are this is just approaching the routing. What is the key of routing operation categories or classical and quantum optimization. So this is the gray wolf optimization. There is a four parameter alpha, beta, and gamma and delta, I mean like that. And based on this hierarchy is basically the first is the leader, that is basically the base of the solution. Second is the level, which is basically the second level of the solution. So you have to also, I'm suggesting to, this is the just a hunting approach, particularly if you are supposed to be know about the behavior of the wolf, how they are hunting, and that the hunting approach is also somehow is to apply in the transport industry. So the all this things is somehow is the real time, or somehow you know about this wolf behavior, you know the many movies and all how the wolf is basically the hunting, and somehow is so you can start your work on somehow as to the hunting behavior, or GSO, which is what exactly, or BHO, what exactly. BHO is a little bit hard because to understanding the somehow is the star density and all black hole and all. But my suggestions to either you could choose the GSO or you can choose a GW or somehow. So here, some of the students are working on this side. You can choose. You can connect with me.